Hello, everyone. So it's my pleasure to do a little summary of what happened in the last 5 years, and then René-Marc will present you what will happen in the next few years. So if I can have the next slide. Yes. Okay. So first of all, I want to highlight a few things about the national coordination of the infrastructure. So because there are some changes that have taken place lately. So I'm here. So I stepped down, last summer from the coordination, and I've been replaced by René-Marc, who will talk right after me. And then in the coordination, we also have several new people. So we have Virgil Vyasnov, who is Deputy Director for National Affairs, who joined us last summer. And we also have Sylvie Gian and Etienne Henry, who will help us to manage the infrastructure and who have already started to work with us. Caroline is still there, good for us. Where is she? I don't know, but thank you to stay. And Alexandre Phillips, I don't know if he's here, but he will step down at the end of the year as well. Okay, so the summary for the last period, for me, so the most important thing was to build a sustainable infrastructure, which means an infrastructure that we can rely on in time. We know that will still be there in 2 years from now and in 10 years from now as well. So when I started in 2019, so Jean Salamero was heading the infrastructure. So we got an evaluation by an energy, which was positive, and that enabled us to get 3 million for the last 5 years now. And then later on, we also made audits by our scientific area advisory board. We also got a positive report, and that enabled us to get a strong support from the CNRS, which is the supervising body for the infrastructure. And again, in 2024, we got another evaluation by, again, energy for the end of the project, which was positive. So we got money for the next 2 years and also a big grant for equipment all over France. And for those of you that are interested, the money is there, so you should receive it in the very few days. On the support from the Ministry of Research increased over the last few years. So this was important because the infrastructure was created in 2011, so 15 years ago. And for a long time, it was not clear what these objects were, what they were going to become. And the support from the CNRS and the Ministry of Research was not always very strong. So I think this is something that we have solved now. We have a strong support. We have a vision from these bodies, for the infrastructure for the future. So this is very good. And we have some plans for the future that René-Marc will present you. Okay, so this is for the institution. And for money, so in the last 5 years, we applied to 12 large projects, from different kinds, European, international, or national. Large grant, meaning from 1 to 15 million. So we had some decent success. 4 were funded, 1 as a leader, but still the largest amount of money come from national calls. And I think this is something we need to improve, is to be more competitive for European calls and also from other international calls. So we can get money to develop technologies and equipment and etc. Okay, so the most important thing, I think, for a sustainable infrastructure is the human resources, because we need people to work in the framework of the infrastructure, so at the national coordination. So as I said, I think we can be very pleased that to have these new people that are coming in on helping to strengthen the management of the infrastructure. And then in 2019 also, we decided to appoint a mission officer, which were in charge of developing specific action that we thought were strategic for the infrastructure. So these were Pauline Paul Gilotto and Emmanuel for data management, Cédric Matthews for the integration of different facilities, because of course we are distributed all across the national territory, so we need to have a common way of functioning at the facility level. Etienne Henry for the technology transfer from the research and development team toward the facility, Fabrice Cordelière for the training, and Jean Salamero for many things, but in particular the relationship with other infrastructures. In particular, he developed the Club des Infrastructures, which regroups not only macroscopy infrastructure, but other large national infrastructures in proteomics, sequencing, animal stuff, different things. And this was very important also to make our relation better with our institutions, because we can speak with a common voice for our needs. So another important thing we did was to hire a communication officer, because indeed, so many people use the infrastructure, but they don't know that they use the infrastructure, because it's their local facilities or the facility in the next city, so they just go there and use it, but they don't know that it's part of a larger infrastructure, and that this large infrastructure is important to develop some key action that I will present rapidly, and also to get money, for equipment and stuff like that. So this is a very big issue, to communicate better to the users, also to the institution, and also to the engineers of the facility themselves. That's important as well. And then we also recently have a business developer to develop usage of the infrastructure by private companies, and it's Sami Al-Borgoul that is in charge of that. So these people, they spend a lot of time working the infrastructure, and they were helped by what we call working groups, which are either dedicated to specific technological fields or to the core facilities, the problem that all the facilities have in running, giving access, training on different things. Okay, so in the last 5 years, so thanks to these people, several key actions were realized. So in terms of data, for data management, so we have developed a data management plan for facilities, and we have developed tools for to access Mesocenter relatively easily. So that was Guillaume Gay. Also, Jean-Yves Tinvez and Anne-Sophie Massé, they developed what is called FBS, which is a remote image analysis service that anybody can use. And also, we developed challenges to boost tool development, in particular with regard to data analysis. And the people in charge were Emmanuel Fort, Thomas Walter, and Doran Kaufman. So you will hear more during this afternoon about this. The second was to boost access to high technologies, which is the key issue, because that's our endpoint mission, is to be able to provide technology to users on high-end technologies if possible. So we did this through access calls, which had a great success in the user community. So some were calls that were made by Euro-BioImaging, but we just put some funds there, or the CNRS. Others were calls that we did ourselves. And these calls are very popular, and many people benefited from them. Several tens of people could access FBI technologies thanks to them. And then a second aspect of this access to high technologies, again, is outreach and communication. If you have a nice technology but nobody knows about it, it's going to be not very much used. So it's important that we can explain to the people what these technologies are, and how to access them, and what problem they can help to solve. Then we had action about to develop technology. So we had some internal calls, to bring up to scale technologies so that they can be used in facilities, by in a more user-friendly way. So we funded in total 23 projects for 1.8 million euros, and that was very useful to strengthen the links between the developing teams and the facilities as well. And for training, Fabrice Cordelière and the working group for training developed reusable resources that are hierarchically organized for training, which I think will be very useful for the future for the facility to develop their own training program in a homogeneous and a very rational way. And then with Cédric Matthews and also the working group for facilities, they spend quite a lot of time to develop common tools for the facilities and to build FBI community spirit and identity across the facilities, which I think is very important. Okay, another very important thing that happened in the last 5 years is that initially we were 5 nodes in black here, so we had several calls to bring new nodes in the infrastructures. Now we have 5 more nodes, Alsace in particular, who joined 2 years ago now, yes, something like that. Rhône-Alpes, who joined recently, Toulouse, Bretagne-Loire, who joined in 2020, and Normandie also, who joined very recently as well. Okay, so my personal take on the last 5 years, this has been a very positive experience for myself. It was really a pleasure to work within infrastructure and meet many very interesting people, encounter new technologies that I didn't know about. And it was also very positive because the infrastructure gained strength. We are much more powerful now in many different areas than we were 5 years ago. And we grew roots in the engineer communities. Among the users, more people use our service than know about us, and also in the institutional landscape, national and international, as I said before. And so we did some important service-oriented action. And one important thing that I want to highlight is that some of this could not be done otherwise, because even for a big regional facility, it's too broad, but we can do it because we have a national scope and we have specific funding to do it, so we can do stuff that are really interesting for the entire community. And one of the reasons why this worked well is that I think we have shared objectives. We know where we want to go, and this is highlighted by our motto: innovation, so develop new technologies; training, so that people can use these technologies; and access through the facility to these high-end technologies. And almost as important as the objective is the values we have. I think also the infrastructure functions very well because we also know how we want to achieve these goals. And our common values, if I want to name a few, is ambition, to develop really powerful and novel technologies, commitment to others and in particular users, professionalism, and of course a passion for microscopy. And then I will leave the stage for René-Marc that will talk about the next years.
Thank you, Edouard. And I think we should all thank him and applaud him for the work he did for so long. In addition, I think we can thank also Alexandre, who is not here today, but that will drop down soon, and that was very also instrumental for FBI, I think, and you all realize. And also Jean, that is somewhere, that is still here in a very, very involved and helping us and helping me also to take this. So it's quite a challenge. For the future, Edouard presented you, but you know already the structure of FBI, the goal, the achievement, and everything. But now there is this new layer, this new thing, which is, I would say, a new layer, but it's not a new layer, is a function, this UAR, Unité d'appui et de recherche, so support and research unit that was introduced, that will coincide, that will be, I would say, on the side of FBI to help FBI to continue and on a sustained manner over years by having the staff and the administrative environment to sustain its activity. And so it's a busy slide, but we can rediscuss and it will be distributed to you. Here is the organization of FBI, and Edouard did present it very, very clearly. And on the side, you have the organization of a unit, a CNOS unit, that will be also co-headed by Université de Montpellier and likely by INRAE to start, but this could evolve, and with a director, deputy director, general secretary, and all people. And you will, of course, find many of the same people on both sides. And I know it's quite difficult to clearly state it, but this is for basically the administration and the part of the research development that it's really shared by what around the action that FBI had started at the national level. In addition, I would say, and together with all what you are doing on your own node for the community. So this creation will be starting 2025. It has been already evaluated by CNRS quite nicely. And what is important is that we will have every year, we hope, a running budget for the activities for running FBI, basically. Not for of course, you see this sum and you see what Edouard presented you. This will not be, I hope, the only budget that FBI will get, and we will need to apply for calls, national or international, to continue our action. And also, but this is a detail, but it's important, there will be some changing in between our governing body to have what they call a GIS, to be able to transfer money from one side to the other without so many trouble that we had so far. So it means that there are people that will belong to this UAR, and there are the names that you already saw with the director, deputy director, general secretary, administrative assistant director. And there will be some mission officials that will be also part-time affected to this UAR. And some people here, quite a number of engineers that you know already, that are so far that have been paid by FBI so far on the action we'll see on the next slide. And some of them are or will be very soon hired by a governing body like Université de Montpellier for Guillaume Gay, INSERM, or CNRS for other, and the hope, what was built over years with the Equipex call that was, or the application to the Equipex is to have a part, to have these people at the end maybe fully on a more permanent position. Okay, so now, with this tool, we hope and we want to continue the action of FBI at the national level. So again, FBI UAR Core is not FBI. It's a part of FBI that will be in support of FBI. So the FBI data, which is quite well advanced, thanks to Perrine, Emmanuel, Guillaume, and all the other people that are involved, engineers involved, with still the same goal that Edouard presented to you, which I think it's not an easy task, but things are progressing, and there have been some, for example, some servers that have been bought very recently to really start to launch all this central management and access to Mesocenter. The FBIAS, which is animated by Jean-Yves and Sophie Massé for image analysis support, and with some also engineers that are affected for most of the time to this work, and also the development of the new tools or through this challenge that have been organized already once by Emmanuel Faure, Guillaume Gay, and Dorian Kaufmann, and this, of course, is going to increase. For the innovation, I think with the tiny budget we have so far, we are still able to continue the tech transfer call. And we have a budget for next year, for 2025, that could allow us to fund 3 to 5 projects, depending the money or depending on the evaluation, I would say. And also we will keep this long year or field the low call for things that are very urgent. We have also a very important tool in FBI, which are this working group of most of you are belonging to one of this working group, which I think are very important to strengthen the relation between the core facility and the team, the R&D team. And of course, like techniques are evolving, some are brand new, some are maybe becoming more classical, and also some thematics are evolving. And for example, there is a new working group that was just built on mechanobiology that also means that we are dynamics and evolving with the technique and also with the thematics. As I was saying also, we need some more money, and it's important. And I think we have to continue and will continue to support application to national or international code, to connect to international code with other infrastructure. Also, as FBI or part of our people in FBI should be involved in more national call. And just as an example, and I don't know to what extent this will have an impact, but as a unit, a CNRS unit, the people, the engineers that are part of this UAR can apply in the name of the unit, I would say, of the UAR, directly to ANR call to be co-partner of teams for ANR call. And also one thing that some UAR are using also is that we could have, if we have the mentor for this, and if we have the money, we could have PhD students that are directly the PhD student of FBI UAR core. So this could be an opportunity for some of you, and I hope it will be used. The training. So the training, we have things continuing, but we have also new things. I think we have a very good opportunity with the arrival of a new node, Normandie, which is, I would say, well known, at least in France, for its initial training activity. And I think that among all the engineers that are here, many of you have been trained and initially at Normandie. And I think this is a very important new skill or new competence that the node will gain with Normandie. And also we have this also lifelong and initial training initiative that was headed by Fabrice Cordelière. And we hope this year there will be the finalization or next year, and online publication of the first MOOCs that are already produced, I would say. And unfortunately, the only block is, as usual, some kind of administrative blocks. So I hope we'll be able to solve it. And I did put it here, but it's more large. We have also quite important action that could be done with the interaction with Africa. For the access, so the call for access for external user will continue, and in the budget of the new unit, we have a specific line that will be dedicated to this. And in addition to this, we have reflection and action on the evolution of what we want to be the most visible as services presented by FBI, and this on a renewed website on which Caroline is working hardly for the website. And also, as Edouard already mentioned, we are in the process of increasing our visibility toward industry and private company, but these are, I think, two different things, and we have two different public, and we need to adapt to these two different public. For the first point, for the call for the access to increase the access, we can, I think what we didn't use so far, I think even locally, is maybe to be more involved in the grants that are proposed or the applications that are proposed by not only the R&D unit, but the team in our environment, and basically to appear as a partner of this team, of this project. We will have the France-BioImaging access funding through this UBI portal that many of you know. And if you don't know, you can come to us or come to Caroline. And we have also here saved some money for this. And it's about a few less than €1 kilo, but it's quite important for basically paying the fee of the use of the instrument. And also there is some more European call then where you can apply for I would say bigger funding and fundings that will also apply for the mission, for the housing, and so on. And so everything is on the website of FBI, and this will not change. This will continue, and we hope we can strengthen it. So for the evolution of service and the visibility of the offer, I think one effort is to render the offer of service more visible. So like on the front page of FBI, in addition of all the offer you propose on each of your node, and this we will try to direct it to, I would say, more high level, more unique, I would say not high level, more unique services. And when I say services, it's not saying instrument, but saying instrument plus competence and so on. And that so will be highlighted for our external user and also your national and international user. So we will also have to increase the visibility toward industry, private company, and user. And this is Sami Albourgol job, and I have a specific slide on this. And also we have and Caroline, I see her as a started to work on the evolution of the website that will go together with the evolution of the offer of services. Okay, so to speak about the action that Sami is doing, so the story was initiated by a call, I think 2 or 3 years ago now, by CNRS to hire transferred engineers in many infrastructure along France, and FBI succeeded in the application and was able to hire Sami, and this basically is in I would say a general schematics where basically you have the goal of France-BioImaging, which is to transfer, to develop, to valorize imaging. There is also CNRS that wanted, and I think that still want to open more the infrastructure to the industry, and also this was I would say directed by the ministry also to increase the relation between industry and public research. And so I think I think in maybe at the next meeting, Sami will be able to summarize or to make to explain you what he achieved in this direction. So only 2 slides now. I want just to remind you that FBI is also part of a more global European or global network, and we still are very involved in Euro-BioImaging, and Yves and Caroline are the people that are really instrumental in making, in pursuing this talk in between the two. And we are the French node of Euro-BioImaging, and each of your node are like this part of Euro-BioImaging. We are partner also of Global Bioimaging. Euro-BioImaging, we have 9 of the French nodes that are already in. of course, the two last ones, which are Normandie and Rhône-Alpes, will need to apply, and they are doing this. It's with the help of Caroline and Yves. It's quite a big application, as I understood. So we will be clean with this. And just to finish, two messages. I think for the promotion of FBI, you are the best, and you should be the best. All the engineers in the platform, all the R&D team should advertise. And I would say the first thing is to say to your user that they are in a FBI infrastructure, that they should cite FBI, that they should promote FBI, and that they should know at least that they use FBI platform or FBI-related platform. And the last thing is that we are very pleased to welcome the two very new nodes, which are Rhône-Alpes and Normandie. Of course, Strasbourg, Alsace, and Toulouse are still new nodes, but Toulouse has been hosted the meeting last year, and Alsace does it this year, and we will know everything about Alsace. And we hope in the next year to be able to visit the two new ones. Okay, thank you, and have a good meeting.
So, could you download, yes, my presentation? So I'm happy to be here to present you this Alsace node. We have been joining in February 2023, so it's quite recent still. And our aim is to perform an integrated development of innovative molecular nanoparticular probes with advanced microscopy. So our node, in a nutshell, now it is working. No, c'est celui-là. Ouais. So in a nutshell, we have integrated all the 6 life science imaging facilities which are scattered over Strasbourg, Illkirch, and Mulhouse. So some of you have been visiting at least the one of Strasbourg or Strasbourg Center or Illkirch. And we are covering imaging from molecules to small animals and plants. So we have the full range of microscope which allows this. We have together 6 internationally recognized research and development teams which are specialized in chemistry, physics, or soft developments. Another strength of the Alsace nodes, it's that on our back we have 7 large institutes. So each of these institutes hosts one of the imaging facilities. There are 7 because one of the facility is split into 2 labs. So these large institutes have international visibility and a very strong and diverse community of users. So you will see it's going in all directions in biology. And in terms of technology and methodology, we have several ones which are unique. I don't go to read all of them. We have 3 in chemistry. We have a few in physics with a certain number of instrumentation which are very specific to our node. So to give you a bit more detail, so here you have the 6 core facilities, and here you have the 6 research and development teams. So as you can see, the core facilities, which are associated to big labs in each case, they are going in very diverse direction in biology, so information in immunology, neuroscience, in vivo imaging, multi-scale plant imaging, here life molecular and cell imaging, biomaterials. And the 6 research and development teams, you have a color code. So the red one are those who are in chemistry, the blue one in physics, and the green one in soft development. So you have 2 teams here Loïc Charbonnier and Andrei Klimchenko in chemistry, myself, Olivier Berlet, Siva Leclerc in physics, and Bruno Claholz in software development. So in terms of core facilities, so you have 4 of them which are in the city center. You have 2 of them which are in fact grouped in a single facility, which are in Ilkirch, and the last one who is in Mulhouse. So it's not so far apart, but it takes some time to go from one to the other one. The most far apart, of course, is Mulhouse, which is in south of Alsace, but the train is quite fast to go there. So just a few words about the governance. It has been changed quite recently. And when I say quite recently, it's super recently, because Vincent Mayoli has been now elected as a new co-head of the Noeud, and he has been validated last week by the Bureau Executive of France-BioImaging, so it's very recent. And another big change that we have is that we have here for the Alsace Noeud core facilities to head them, we have Pierre Henner, who will have the super difficult task to substitute Bertrand Vernet, who has been super involved and super efficient in promoting everything during this year and gathering us all together and making a lot of action. So I really would like to thank him for his past action. So thank you. So we are very sad, but Marseille, who will now gain Bertrand, is very happy. They are already celebrating at the Canebière the coming of Bertrand. So, but Pierre Henner will be certainly doing a very great job as well, but we have to reorganize a bit to compensate the leave of Bertrand, and also to reorganize as a function of the new organizations that you would like to implement. So for the facilities, one more point. So these are the key facts. I don't go to bother you with all of these numbers. So you have the instruments, the machine hours, the users, the investment we try to get every year, the publication. We have quite a lot of training, and this was also one of the activity of Bertrand. He promoted a lot the training on image analysis. We have now many courses which are now going quite well, and each time there is quite a nice number of people who want to attend them. We are doing some networking as usual, GDR, IMABio, RTM-FM. We have also this cross-border MIAP, which is quite more specific, and we have also we are participating notably in MIFOBio. So in terms of instrument, I will not bother you with the long list of instruments, just to show that in our core facility, we go with the researcher from the research project. We make some accompaniment with research project until the analysis. And in terms of scale, we go from the molecule to the organelle, organism. And of course, we have the microscopes which are suited for each of these scale, which are available. Concerning the research and development teams, so these are the numbers. So quite a significant number of people are working in these teams. They got quite significant competitive funding, large number of papers, patents, and recently even a startup appeared with one of these teams. So now I am just doing some teasing, because tomorrow you will have more details about all of these teams in the different talks. So the first team is the team of Andrei Klimchenko, chemistry team. They are developing innovative molecular nanoparticular fluorescence probes. So on the level of the molecular probes, these are mainly for biomembranes and organelles. They develop quite a lot of them. Also RNA aptamers, membrane receptors, probe for membrane receptors, and they are developing also very bright fluorescent nanoparticles, which contains a very large number of fluorophore inside. So that's why they are very bright. And they made a lot of application, nano antenna for RNA DNA detection, biosensing and bioimaging, even in small animal in imaging. And they build up this bright sense startup. The second team, also chemistry team, is the team of Loïc Charbonnière, who is working on up-converting luminescence probe. You remember this is the one you excite in the infrared and you get some visible light out of them. So you have the classical UCNP, up-converting nanoparticles. So they have been working on them, they are still working on them. They are doing some special surface photofunctionalization. So some lanthanide-loaded polymer, UCNPs, they have been using. And the very specific part in their team is to work on this molecular upconversion, which is a very challenging strategy because they want to narrow down the size to the molecular level. And of course, it's quite difficult to get them bright, especially in water at this scale. The third team is my team. We are developing an instrument for new fluorescence probes. This is just a few of recent development we made. So we have been developing this spectral paint where we have both localization, super localization, and for each of them we have the spectra associated, which means that we have an environment sensitive information at that level. We have developed this DRET paint, which is dark resonance energy transfer. So we have a probe which is used as a dark, meaning low fluorescent probe for doing the donor. And this gives a very low background, and that's why you get a fast acquisition with them. And we have here some older setup we have developed, the 2-photon microscope, which we have been using with these 3-hydroxychromone dyes, which have been developed in the lab, where we have been using them for ratiometric 2-photon imaging and FLIM images as well. So the next team is a team of Sylvain Leclerc. They are physicists. They develop advanced microscopy techniques. And one of the most fancy one is this one, this multi-well plate imager, so which is based on oblique plane microscopy, so with light sheet imaging and a single objective near the sample. And this is just an application for monitoring the glucose dynamic in a tumor spheroid. Another team is a team of Bruno Clauls. They are developing some super resolution techniques. So they are on the side more on the electron microscope, but they are also doing some optical microscopy as well. And they have been developing a number of software. Perhaps you may already know some of them. And they are for super localization and multicolor super localization. And the last one is the team of Olivier Oberle from Mulhouse, and he is, in contrast to the name of to the main target of our node, he is working with non-labeled biological sample, and he developed this 3D tomographic diffractive microscopy. He was the first one to provide the proof of concept of this tomographic diffractive microscopy. The lateral resolution is below the diffraction limit, and now they are improving it in many directions to have a better resolution, isotropic resolution, and to follow it in 3D real time. So just to say also that we have since a long time already quite used to work in a good way between the core facilities and the research and development tools, and that have been a certain number of transfer of technology which have been already done. So again, with this team of Olivier Oberle, they have been developing this differential spinning disk confocal tomography setup, which has been transferred here at the IGBMC. They are still working on another development in the same field, and again with the aim at the end to make this technological transfer. The team of Andrei Klimchenko is quite active as well, as you know, and he is working with the in vivo imaging platform of the CRBS. So as you can see, with the nanoparticles they have been developing, they had made a lot of application for the in vivo imaging. Here in mice, here you have extracellular vesicles. In vivo, they have been targeting tumors, they have been doing barcoding and in vivo tracking. So quite a substantial development which have been done and applied. On our side, we have been working with this imaging platform which is called Quest, which is in Ilkirch, and together with some teams in Italy and the US, we have been involved in the design of optimized fluorescent nucleoside analogs, which are substituting perfectly the guanines. And we have made extensive photophysical characterization of them, and we are currently developing 2 setups for monitoring them, either at the single molecular level or at the cellular level, using the fluorescence of these fluorescent nucleoside analogs. So we have been also involved together with Loïc Charbonnier and Thomas Hirsch. So Thomas Hirsch is a guy who develops a UCNP, but very advanced one. Loïc Charbonnier, as you have seen, he's in the molecular up conversion. And to support their development in chemistry, we have been building up these setups, which are anti-Stokes microscope, either in the confocal mode here or in the wide field mode. And this is the kind of image that you get when you follow the single UCNP. And we use them also for application for tracking, a very long-term tracking, because they, as you know, UCNPs do not photobleach at all. Another specificity of Alsace is that we have a quite rich ecosystem of local nodes of other national infrastructures. So for instance, you have FRISB, which is very strong here in Strasbourg. We have also France Génomique, which is present. We have Profi, which is in the proteomics field. Fluorescence life imaging, which is in the biomedical imaging, and Phenomene, which is in the phenogenomics. So we have quite already a lot of interaction with them, and this is probably a strength also. And as you have may noticed, we are not so far from Germany here, and not so far from Switzerland as well. So that's why we have some links with the cities on the other side of the border. So Karlsruhe with the KIT, Karlsruhe Institute of Technology, Freiburg University, Basel University as well. So this is what is called the tree ratios. There are certain numbers of tools which are, or networks which already exist, like Nebias and so on. We are also involved in certain number of cost action as well. And finally, to conclude, so to make a summary of all what I present, so I hope that I convince you that we have a certain number of original innovation in the chemistry fields, in the probe fields, which are supported by ad hoc imaging techniques and data analysis. We have 6 core facilities which are hosted in large institutes with a very broad range of biological research. We have a very close collaboration with national infrastructure nodes, and we have a chance to be close to the border and have some preferential connection with international institutes, and we are kind of head bridge with Germany and Switzerland networks. So this is what I could try to tell you about the Alsace node, and of course we have time during these days to exchange and to give you more information about it. Thank you for listening.
So hello everybody. So it is a great pleasure for me to be here. So in order to present you the Normandie node. So in my presentation, I will show you and explain the composition of the node, and so how specific scientific and technology signature and how we interact with the different working groups and France-BioImaging nodes. So, sorry. So So the Normandie nodes comprise of the three main Normand universities, so L'Université de Rouen, Le Havre, and the University of Caen. It comprises 7 partners, which implicated 65 people and 30 imaging devices. So all of this equipment and people are distributed in one imaging facility, which is Primacen, localized in Rouen, and 6 research and development teams. So 4 research and development teams are located in Rouen, 1 in Le Havre, and another one in Caen. Sorry. So here we just summarize how we are currently implicated in the the different working group and the executive board of France-BioImaging. So in the executive board, so Ludovic Gallas, Damien Chapin, and myself. So we are implicated in the BE. And so different people from Primacen are also implicated in the different working package and groups. So for example, so you have Damien Chapman, who is implicated in the integration and core facility, Christophe Chameau in the FBI and training, Alexis Lebon in the FBI data, and Magali Bénard as our community manager. She's implicated also in the Africa Pole Joint Initiative. Marc Ropito and Sophie Bénard in the CLEM group, and Delphine Buren and Ludovic Gallas in the master. They are in charge of the master in cell imaging. So in addition to this implication in France-BioImaging working group, so all of these people from Primacen are also implicated in the different imaging networks in France. So as you can see here, so different people are implicated in the, for example, RTM-FM. So Damien Chapman will be the next coordinator. So he's also a member of European Light Microscopy Initiative of the FLIM-UV. So you have also different people in the RTM-FM and different members of the electron microscopy network. And so there are also people, groups, teams also implicated in different national infrastructure, like France Life Imaging, so there's 2 research and development teams, and so Ludovic and Magali are also implicated in the infrastructure and Ibiza. So now I'm just going to explain to you and show you the facility, and after we'll talk about the research and development teams. So the imaging facility Primacen, so here you have a mind map of the complete workflow of Primacen. So in the center, as you can see here, so you have a human resources and you have different concentric rings. So first, so in blue here, so you have a different types of animals, plants, and the different samples, so rodents, aquarium plants, so fixed and live samples that we can work on. And after, as you can see here, so in orange, we have a different type of microscope and imaging that we can perform. So, and as you can see, we go from macroscopy to photon microscopy and also nanoscopy and CLEM. And so all of these imaging equipments are also under quality control assessment. And so the last concentric rings, so in blue, is that we are able to develop and program, so in a customized way, the different, with different software. And so we are able to analyze and treat the different imagings obtained from the different imaging systems. So all of these equipment are under the quality management rules ISO 9001, and so Primacen is also implicated in the sustained development and corporate social responsibility. Of course, so this imaging facility is really implicated in the master program in cell imaging, but we will talk a little bit later on, and also part of the France-BioImaging node. So the Normandie node has 4 main scientific signatures. So the first one here is the vascular science, where there's a multidisciplinary fields where we have neuroscience, cardioscience, and ecotoxicology. And so in this field, I will show you some examples just after, but we are looking mainly at the vasculature in physiological and pathological conditions, such like in stroke or inflammation or chronic heart diseases. The second scientific signature of the node is the microalgae bioscience. And so, for example, we used microalgae as cell factory to produce humanized and therapeutic antibodies. And so some of the team are also part of the Institute Carnot, and another team, in Rouen directed, the COBRA team directed by Xavier Franck, also implicated in the Carnot Institute, is producing and characterizing new fluorescent probes. And so you will have a talk of Xavier tomorrow. And so the last scientific signature is the intercellular communication, where we mostly perform super and high resolution, for example, FLIM and STED, in order to decipher synaptic transmission and cell-to-cell communication. And so Magali will talk about her last result also tomorrow. So regarding each scientific signature, we also have specific technology skills that I will show you really briefly now. So regarding vascular science, we have different models, going through animal to human models. And so, for example, in animals, as you can see here, we can go from rodents, different mammals, and invertebrates models. And so we look at the vasculature in order to target, as you can see, retina, brain, heart, and hemolymphs. And so this, we are able to do it at different multi-scale imaging. So, for example, as you can see here, we are able to see the microvascularization of the retina thanks to OCT ERG. We are also able to see the formation of a dissolution of different thrombus in the brain vasculature using two-photon microscope. And so we are also able to see these different organs in their entirety by performing, for example, macroscopy on the retina, and so also light sheet imaging on, for example, the developing brain and on the heart here, you can see here, where we are able also to detect and discriminate blood vessels and lymphatic systems. So in order to improve and emphasize our technology skills, we just get two grants. So 2 grants from the Normandie Council and the European Union. So the first one is to better image the intravital heart imaging. So we are looking at with motion compensation to see the heart beating and to do it in vivo. So we are looking at different propositions, and so we are looking mostly, InScoper will propose a complete proposition going from the acquisition system to the analysis and to be able to obtain all these data in vivo. And so the second one, we also get a grant from the Normandie Council, and so we will upgrade our multiphoton imaging. So we will have a second laser on our two-photon microscope, so the Ultima 2 Plus from Bruker, so to be able to better visualize the brain vasculature, and also to develop optogenetics, and also we have new scientists that are using different nanoparticles, so fluorescent nanoparticles, and to be able to engage them and to see how do they react on the blood-brain barrier. So regarding the second scientific signature, the microalgae bioscience, so we have different ecotypes model like Chlamydomonas reinhardtii, and so these microalgae are able, so as you can see here, to express different fluorescent proteins. And so we have different techniques to see this ecotype model on this microalgae live samples and cryophic samples, for example, with HPF and ISF. And so we are able, as you can see here, that we can do electron microscopy to immunolocalize the different enzyme of glycosylation these microorganisms. And so, as in vascular science, we are also improving our technology. And so so Primasen just acquire and develop a new RT claim and cryoclaim to work with the plants. And so so this system goes from the plant freezing, as you can see here, to the cryoconfocal FLIM and the TEM. So they just received, so as you can see here in October, so the cryoconfocal, and the TEM just arrived a few weeks ago in the facility. So regarding the scientific signatures of our new fluorescent probes, so here you have a complete workflow. So of the production and the characterization of these new probes. So here you have the production by doing so different organic chemistry, and after, in order to characterize the different fluorescence, so we have different microplate readers, and so fluorolog-free, and the Cobra team is also synthesize different single oxygen lanthanide, and so also characterize the fluorescent lifetime with different imaging. But Xavier will talk a little bit more about this and show you his new fluorescent probes tomorrow. So regarding the live scientific signatures of the intercellular communication, so we are performing FLIM-STED and FLIM-STED for living samples. So Magali Bénard, who won 2 years ago the FBI image contest, so she will explain to you tomorrow her new results about this nanotube communications and the FLIM-STED application for these living samples. So now I'm just going to show you the specific networking that the Normandie node have with the other France-BioImaging nodes. So in these few slides, we will show you how we contribute, how we participate to the training, and also how we scientifically interact with the R&D team. So first, with the node Île-de-France-Sud. So, for example, so someone from Primasen, so Philippe Chan, participate to the electron microscopy training, and so Christophe Chameau is going to contribute to the confocal microscopy. And so, thanks to the grant and the access from Euro-BioImaging and FBI portal. So some PhD students, so Thomas Bonds and Sophie Bernard, went to the Île-de-France node, and performed some FIB-SEM with Claire Boulogne and microalgae, which give us some preliminary data in order to write a grant for the first tour of INER. So the second example is with the interaction with the Bordeaux node. So Delphine and Aurélien Debonne went to the training on light sheet microscopy, and so Magali Bénard will contribute to the STED microscopy in 2 weeks, in the STED microscopy workshop in 2 weeks. And so again, thanks to the access through the Euro-BioImaging FBI portal, so some PhD students went to the BIC in order to perform electron microscopy and to study the neuron myelination in the corpus callosum. So the last specific networking that we have is with the Alsace node. So Magali Bénard and Ludovic Gallas, they are working with Mayol Colo. So they are testing different probes that they synthesize, and they're testing it on their different nanotubes model. And so one example of tech transfer that we just got is Christophe Chameau and Damien Chapman, so in collaboration with the Alsace node and the Toulouse node. They are transferring the quality assessment and quality control for light sheet microscopies, so in order to transfer all this technique to the FBI community. And so now I'm just going to talk about the training. So one added and main value of the Normandie node is the training research continuum that we got through the International Master in Cell Imaging. So this master is also called IMAC, and it's and this year it celebrates its 20 years. So this master is also associated with the Finland and more specifically with the University of Turku. And so Ludovic Gallas and Delphine Burel have different perspectives in order to increase and to more communicate with the different FBI nodes. So the first one is, as you can see, here is maybe to identify different students from the third year of their bachelor degree from the different node university that may candidate to the master in cell imaging. And so maybe this student can go back in the different FBI nodes for their internship during their Master 1 and Master 2 degree. And another perspective is to interact and to have more contribution from the other FBI node members. So for example, Christophe Chameau and Fabrice Cordelière, they are working on creating different fun MOOC that they can add on in the master, and they're also looking at the contribution of new FBI node members in order to have the group lecture, to have more specialized people for the different techniques. And so Magali, which is implicated in the Africa-France joint initiative, will maybe interact, and maybe we'll have more foreign students that can integrate this master. And so regarding our international collaboration of the nodes, so obviously we have collaboration with Finland and more specifically with the University of Turku, thanks to the master in cell imaging. And so we are also collaborating thanks to the Maupertus program. We also have strong collaboration with the Japan, and so some people from Primasen went to Japan in the last September, and so we also got different call and grants for access user from Netherlands and from India. So people from this country will come to Primasen to perform some experiment, and so we will also be implicated in, as I told you just before, in the Africa-France joint initiative. And so just to finish, so we have, I'm just going to show you the recent and upcoming Normandie Nodes events. So 2 weeks ago, so some 8 students and 2 staff members from the University of Turku came in order to have a training and workshop on quality assessment and reproducibility for instrument and images in light microscopy. And so what is upcoming in the Normandie nodes, so Delphine Burel and Ludovic Gallas, they are organizing, so in the next February, the HAVE Cerebellum Days. And also in March 2025, so you will have a workshop for the CLEM working group, which will be in Rouen. And so on, and I would like to thank you for your attention.
Pleasure to be there. Some of the people of Grenoble and Lyon were in the kickoff meeting in 2011, but on the other side, and we are very happy now to be there. I would like to thank mostly all the direction and especially Edouard for the support to join us after so many years. And it's true that it has been a long way, but it was a very important process for us, and we are very happy to join with Normandie with a very complementary project. And the interest of this region, it's a second region. There is a lot of research, a lot of different research. And what we firstly check is that not a lot of people knew FBI in our big region. There is not so many users of Aura, not so many FBI users in Aura. And the first thing that we have to do is to promote. And we are waiting for the stickers to put that a little bit everywhere in order to make them understand the big interest and also how it's changed the way to request funding and things, equipment that we have to explain also to a lot of different people. And the second thing, it was also to try to improve the synergy in this big region between these two big centers, Grenoble and Lyon. There was links and we wanted to go further, and FBI was the perfect opportunity to do it. Why? It's because there was two big network on platform where we're bringing all together. We don't want to put all the different platforms that there is. There is one in Grenoble that existed since 2009, and thanks to Yves, who just retired a few months ago, and the name is ISDV for Imagerie de Sciences du Vivant, and another platform from LIMIC in Lyon that get the Ibiza label in 2013. And both platforms, they regroup a lot of different academic teams. They're connected with a lot of medical departments, hospital, numerous industrial partners, and also there is numerous R&D team. And the problematic was to select few of these elements to make something that was highly synergic to what was developed during these 10 years of FBI. And we proposed this organization. First, we have a scientific committee when we are very into the interdisciplinary. There is a lot of different senses of biology, cell biology, medical science. We have physicists, we have chemists, and the idea is to create a mayonnaise between all these different people. And that is also the specialty of Grenoble, and also Lyon is a strong interdisciplinary field, and we are very happy to discuss about that with the colleagues of Paris and also the colleague of Marseille. And with Jacques Brocard, who is present, we are co-directing, and the first thing that we have done is to create an executive board. I'm very sorry, Xavier, I forget you in the train. It's there. There is another member, Xavier Joran, who is there. It's very important. We try to have as much as women as men, because for us it's very important. And we have most of these executive boards have research engineers, and some of them are connected with other infrastructures such as Frisbee, which is also very important because there is a lot of structural biology in Grenoble and in Lyon. And I don't want to forget somebody very important behind. He's not present. He was behind all the time. Is Jean-Louis Bessereau. And when we met with Jean-Louis a few years ago in Grenoble, we said, okay, we have to do something between Grenoble and Lyon. We were fully agree, perhaps because we were not from Grenoble and he was not from Lyon. That was perhaps the occasion. There is also other people behind that are not present. Is Antoine Delon, who is a physicist that we are working for many years, and Gabriel Bidot. And I think also about Dominique Bourgeois, who was very important, and we will not talk about all the possibilities that exist in the Aura region, but we will try to focus on few elements. And we were very happy first to jump into the FBI network. I don't know for you guys from Normandie, but since January we jump into it. We jump into all to the working group, and for us we were building the synergy from the beginning, and we wanted different people from the two sides, Lyon and Grenoble, not only one, two, and we tried to build all of that. The integration with Camilla Lecardini, Cécile Côté, the data management, that is a key element for us, and it's something very important and we are very happy to see that FBI have done so much work on this aspect with Denis, Marine Breuilly, Arnold Fertin and Mylène Peuzet. We are currently pushing for the new working group about developments, and we are bringing new people, and we are also connected with the initiative in Grenoble, the artificial intelligence, the MEI, which is the second big nodes in terms of artificial intelligence after Paris. And we would love to connect them, and the people of MEI are very interested to connect also with us. Why? Because it's allow them to spread with Lyon, of course, but also with Saint-Etienne and Clermont-Ferrand, and it's part of the strategy. And we were very happy to support the node for Afrique. Why? Because there was already initiative in our environment with Aminata Touré. She's a colleague. We are co-leading the scientific platform of our institute, and the newcomers in INSERM, Raouf Issa, is in Lyon, and they team up. And also we wanted for them to provide all the University of Lyon and Grenoble are doing. I'm thinking especially about Grenoble, which is very active in Morocco, Algeria, and recently in Rwanda. And I think it's a great opportunity to bring this opportunity with their personal initiative with Mali and Senegal. And I hope that perhaps that FBI could go further than Africa, and why not about South America? And if Mély spoke about China, with pleasure. And Marine Breuilly, a very important person. She's at different level on the slide, and we really strongly support the recruitment of this person, because she is also joined the dynamic of FBS. Why? Because she's one of the rare experts in image analysis. She's an expert in image analysis, of course, but also she's an expert of diffusing this culture of image analysis that is very important for us. And she created this analysis club in a format where everybody can go, and we push more and more people to just connect, to have these simple habits to go there. And she opened it to Grenoble, and now we go and more we do things together. Okay. That's it. And in terms of training, of course, we try to go in, and I make the promotion of the training that will couple statistical analysis and image processing. It will be in January, and we would love to have the support of FBI. Perhaps it's too short for now, but it's the kind of training that we want to push, and that we will propose to the people of both Lyon, Grenoble, but also for the user of FBI. Okay, that was the beginning of the project. We had a project which was centered on a new R&D, that was R&D development, that was highly complementary to most of the nodes, because a lot of people from Lyon and Grenoble are working for most of you since decades. And we focus on these four axes, metabolical imaging and manipulation, biomechanics, spatial cell transcriptomic, and 3D multiscale imaging. And we made this slide, what is new now since after these few months, and we have some novelties, such as the following. Why we went on metabolic imaging? Because there was a strong expertise in this lab of Grenoble, and it's not something that is not so accessible, but everybody is going about what is going on in terms of metabolism in organism, at the subcellular level. And around this lab, there is other lab, another platform, which is an Ibiza platform from metabolic analysis, and another lab in Lyon who is doing a lot of biosensing. And with this culture, we started to say, okay, we have more and more users interested by imaging, and we have technology that could be completely adapted to it, and especially this new device that we developed with Marc Tramier in Rennes and the company in Scopper, which is to integrate fast FLIM analysis with turf analysis, and that is allowed to improve the signal to noise ratio. And now this machine, we get new fundings to make it evolve to integrate the spinning disk modality. And all this technological environment is associated with a strong environment of optogenetic that have been developed in Grenoble and now is diffusing in Lyon. And the idea is to follow, of course, different metabolic sensor through ratiometric based, and use the FLIM for another type of FRET approach. And we are very happy. since we had the first European users. Somebody from Leuven came and she decided to use the turf-fast FLIM to look at molecular tension, not only in static but in dynamics, and thanks to the signal-to-noise ratio and the low phototoxicity of this kind of machine. In the same time, there is a lot of groups in Lyon and Grenoble. They are very specialized in biomechanics. That beautiful experiments of the group of Laurent Blanchon and Manuel Thierry's labs. In cells, in animal cells, in plants, even in bacteria and parasites, and we'll go a little bit further. There is some companies that provide you some services, and of course we have regular meetings, regional meetings since 8 years, and we will love to make that connected to FBI. And thanks to all this community, we find different people that will join the working group in mechanobiology in Lyon and in Grenoble, and we want also to implement, to bring new people in the field by in order to bring all the modeling aspect associated with the experimental aspect. How could we make new things in biomechanics? Now TFM has been spread a little bit everywhere, and in fact there is some R&D team that are presented that gain a lot of expertise in another way to probe stiffness, such as the V-MembO, and that the group of Thomas Dehoux at Lyon. And of course, there is all the expertise of the AFM in ENS de Lyon dedicated to plant biology, which is another level that the animals. And I will make a small focus on this beautiful development of Delphine Debar in Grenoble, where she tried to couple microfluidics and precise measurement of the thickness at the nanometric scale in order to calculate rupture forces, meaning which is close to adhesion forces, this type of forces that are very difficult to measure, that TFM cannot resolve. Only nanotension probes can do it, and we think about also to bring nanotension. And the people who used this technique, the group of Isabelle Tardieu in Grenoble and Galina Dubacheva, make a beautiful paper in Nature Microbiology of the forces produced by toxoplasma thanks to the ability of this measurement of these rupture forces. And the idea of Delphine, the Delphine is currently developing the same type of measurement with bacteria, with blood cells, meaning with cells producing low forces, but they are still producing adhesion forces. And a very strong axis in the Grenoble-Lyon is also all the aspects related to spatial transcriptomics. There is a lot of company, there is a lot of things going on, especially in Paris and in Montpellier. And the structure that I will present already received an Equipex a few years ago. It's soon available on a platform, and I will show you the different caviar and how the nodes of Grenoble and of the Rhône-Alpes will organize and will make evolve this kind of technology. And the pipeline came from Yann Gavy and Jonathan Enriquez and Dr. Monio at the environment around INS Lyon, EGFL. And the idea was to be able to control many aspects of spatial transcriptomic. In general, what you do, either you go and you buy some chips, very expensive with companies, and either you try to do this kind of thing that have been developed. It's derived of merfish, a little bit different in different places in the world. And what this consortium made, they made a strong effort to control all the barcoding processes and chemistry. Why? Because they want to change the type of organism that they want to analyze. In the companies, you have mostly human and a mouse, but if you want to do cricket or Drosophila, nothing. All these people make a strong effort about controlling all the barcoding and being able to produce different barcodes for different organisms. They made an optimization of the measurement of these different barcodes in 3 dimensions. And to optimize also the sensitivity of the detection. And also they work about processing all this very heavy information through a dedicated cluster analysis. When I presented in January this slide, there was 11 genes detected, and now they go, it's something that just came 2 days ago. You have an imaginal disk of a Drosophila that you can detect with 3D MERFISH with an Aberrier Infinity confocal microscopes. And you are able, through this 6-channel analysis, to encode 15 genes on this, I don't know the voxel, it's around 200 meter 300 thickness, 200 micrometers length, etc., etc. And the idea is that they are able to solve these 15 different genes and their position in the imaginal disk and recalculate if which cells express which patterns. And they're currently working on the precise pattern development, and it seems that it fits. And the idea is that we want to go to capitalize on this expertise to go a little bit further on the spatialization of the multi-omics. Why? There is other interests, such as the spatial metabolomics, and also in being able to have something super, I would say, dedicated to research, and something that could be more related to clinical aspect. And the questions are in general the same, but in general, the people are not speaking to each other. And we try to create under the supervision, under the, not the supervision, and under the help of the Clara, the Canceropol Clara, who is very interested into that. We are trying to bring all the community all together and to fuel also what is going on FBI. A novelty, we have developed for many years this prototype, not us, it's Antoine Delon and Alexei Grishin at IAB, of integrated adaptive optics in a confocal microscopes. And now with Florence Apec, they develop like a pipeline where you can acquire big structures such as an embryo or a tissue with a very simple light sheet, not very highly resolutive, like the leaf system. And after you come back to the same pieces and you are able to go to the cellular resolution. And in this case, you can see beautiful nerve precursors associated with dye staining in this beautiful embryo. And it's a little bit the pipeline that we want to implement and stabilize. And it's a pipeline that we presented to the last JDR meetings. And some of you have tested these different technologies separately, but now they are connected all together. And now, thanks to the PLAT team and the exchange of material between Lyon and Grenoble that FBI helped in a way, we have been able to integrate the 2 photon modalities on this system. That is another example on testis, and it's an example of synergy between Lyon. We went to the light sheet in Lyon, came back, do the image, do the adaptive optics confocal imaging in Grenoble, and this researcher made this very nice paper in eLife. The interest in FBI is, of course, we have a strong interplay for many years. We want to connect, as I told you, all the users of Aura to the FBI possibilities and to integrate that, because a lot of head of unit, they did not integrate it, that it was another way to do science and also to think in terms of financing equipment in their own institute. Of course, we want to propose original transfer technology and also to support the research and development team. We are very interested in all this bioimage storage analysis. We want really to go into that in a professional way. We have talked for that for many years, and now is the time of action. And thanks to FBI, it's possible. And the idea is to participate to the training of Euro-BioImaging and, of course, increase the international visibilities of all the people and all the team of Aura. And now the next move is Euro-BioImaging. Thank you, and we have the pleasure to do that with Normandie.
Hello, everyone. I'm Marianna Childress Poli, and I'm the communications officer at Euro-BioImaging. And on behalf of my colleagues at Euro-BioImaging, I'm here today to present to you opportunities from Euro-BioImaging. And before I get started, I want to thank the organizers for this really lovely meeting. And I'm looking forward to talking with everybody this evening as well. And thank you, Caroline, for the opportunity to present today. So, what is Euro-BioImaging? As you know, Euro-BioImaging is a research infrastructure consortium or an ERIC, that is dedicated to providing open access to imaging technologies, expertise, training, and related services. We're publicly funded by our member states, which you see here on the map in green, and we are operating as a gateway or a central access point to 237 of Europe's most excellent imaging facilities. And these facilities are organized into 41 nodes, and France-BioImaging is one of Euro-BioImaging's 41 nodes, and you have your own node system behind, organized similarly to us. Euro-BioImaging is part of an ecosystem of research infrastructures. These research infrastructures are similar to Euro-BioImaging on the European level. They offer access to services that support life science researchers. This can range from biobanks to drug compounds to structural biology imaging services. And many of you already pointed out the different infrastructures that you're working with nationally, and we're similar to you working with these infrastructures on the international level. But why do research infrastructures matter? And why is it important for France-BioImaging and other national imaging communities to be part of Euro-BioImaging? I found this quote from René-Marc Mège to be quite a nice insight into why it matters. It matters because together we are driving scientific progress, right? By offering open access to imaging. And this is really making a difference because we're pooling resources, we're sharing knowledge, we're working together to strengthen the European research area. And it's really making an impact on science. And so at Euro-BioImaging, we're all about user access, right? And since Euro-BioImaging started operations in 2019, there have been 772 proposals received through our website. And France-BioImaging is a really big contributor to that. So as you can see here on this, and you can, I guess we can already say, congratulations, pat yourselves on the back, and keep up the good work, because this is really, really important. And so you can see that there has been steady growth of users from France-BioImaging, so a total of 108 since we started. And then with regards to the other biological imaging nodes, France-BioImaging is clearly ahead. So keep up the good work, keep talking about France-BioImaging, raise visibility, and bring the users to all of us, because that's what we're really about. Another thing that we are really involved with at Euro-BioImaging is image data services. And Edouard was talking earlier about our common missions and our values. And I thought, wow, what he said is so true for Euro-BioImaging too. So we're echoing and we're working together on a lot of the same topics, right? So at Euro-BioImaging, all of the nodes are offering image data analysis, and sometimes as a standalone service. And France-BioImaging is really a leader in this domain. And you guys are really organized. You're already pooling your resources. You're working together as a community. And you're a real benchmark for the rest of our nodes. And you should, it's really good that you've published your paper about FBIs and that we can get the word out about this, because it's a benchmark and an inspiration for the rest of our nodes. And at Euro-BioImaging, we're trying to do something similar, but on an international level. So connecting imaging analyst communities together. And beyond that, we're also working on fair data workflows and pipelines, and working to provide tools to make data fair. And this is the work of my colleagues Asta Matur, Bugra Özdemir, and Isabelle Kemmer. And I'd share just one quick example of what they've been doing, but if you scan this QR code, you can visit our website and you can have an overview of a lot of the resources that they've been working on. And here's one concrete example. This is the FAIR image data analysis tree. And it's basically a step-by-step process to choosing an image data repository for your FAIR data. And it's out there on Zenodo. You can download it by scanning this QR code, and you can share it with your users or just use it for your own work. But this is an example of the kind of tools they're working on. In addition to that, Euro-BioImaging Hub team is really working to on the European level for lobbying and raising the visibility of image data analysts and their work by membership in the EOSC Association, participation in the task forces there. We're also working to coordinate various EC-funded projects. A lot of them are focusing on data, so metadata standardization, cross-domain data compatibility. And then, of course, we're just like many of you, we're also part of the international community initiatives where people are talking about data topics. One example of these data projects that Euro-BioImaging is actually coordinating is AI for Life. And this project is a bridge between the computer science world and the life sciences world. And currently there's an open call if you need deep learning help with some of your image analysis workflows or pipelines. This is the place to go. Same, you can scan the QR code to learn more, and you can apply by December 10th if you're interested. Another project that focuses a lot on technology development and data analysis is the ANERIS project, and this is Perrine working on it. Within France-BioImaging, Euro-BioImaging works together with France-BioImaging, but also the University of Haifa. There's a lot of developments going in AI and so forth for image analysis and underwater image analysis in particular, I believe. And there was a big successful workshop last year, which continues to gain visibility on the Euro-BioImaging YouTube channel today. And the next edition of that workshop takes place December 2nd and December 4th. So if you're not aware of it, I would encourage you, and you're interested in the topic, please sign up. It should be really, really good. So yeah, what's in it for you here? So basically, as you see, Euro-BioImaging is working on the full pipeline towards fair data, just like you. But we all can work together and connect communities also with other nodes within Euro-BioImaging that are working on these topics. And then in parallel, we're working on the European and global level to develop best practices, get funding, and continue to raise visibility. So one of our biggest success stories is getting EC funding for these projects, which are called TNA projects. And the 3 TNA projects we're involved in are pictured here. France-BioImaging is part of all of these projects, which means that these are real opportunities for you and your users. Altogether, it's 1.4 million euros to support user access at all Euro-BioImaging nodes that participate. And currently there's 2 open calls that you should know about. One of them is for any users working on plant biology topics, agroecology, and I heard several of you talk about plant biology applications earlier. This call requires working with 2 different infrastructures, so imaging services from Euro-BioImaging, but also maybe phenotyping from another research infrastructure or different services that are part of the catalog. A pre-application can be submitted by December 5th, and it's my colleague Ayoub El-Gadraoui who's running this open call if you need more information. And then CanServe, this call is for early career researchers working in the cancer field. It's access to imaging services at Euro-BioImaging, at France-BioImaging, but also up to 400 services offered by other research infrastructures. So really supporting research and training in this cancer challenge call. CanServe. Another really important project for Euro-BioImaging funded by the EC is the Evolve project. And in this project, it's basically the Euro-BioImaging Hub team, the 3 entities of the Hub team that make up the consortium. And the idea behind this project is to strengthen Euro-BioImaging. And strengthening Euro-BioImaging means strengthening our nodes. So there are lots of opportunities for you in here. And maybe you saw the open call for job shadowing that opened earlier this year. That was the first activity via the Evolve project. Basically, it provides funding for node staff from one facility, let's say Alsace node, to go work with colleagues in Sweden at a Euro-BioImaging node, for example. And we got 24 applications for this program, so that's pairs, right? The visitor and the host apply together. And they were from 11 countries in the EMBL, 21 nodes participated, which is really good. And overall, there were 12 successful applications, one from France-BioImaging. But the call will open again in 2025. So if you didn't know about it this year or didn't have time or didn't have, a pair in mind, you've got time to work on that. There's going to be another round. Currently open with the Evolve project is opportunity for up to 3,000 euros funding to cover your registration fee, travel, and accommodation expenses to get training. And this is training on microscopy topics, also facility management topics. The training courses can be run by another Euro-BioImaging node or by an external. So this is a really excellent opportunity if you're looking to advance your career. The deadline is January 31st, and there's information on our website. I just realized I forgot the QR code. But you can find, there's a news article about it if you look for it. And another opportunity from Evolve and the Euro-BioImaging data team is the Image Data Community Days, which will be taking place virtually in 2025. The registration isn't open yet, but we are collecting interest. And here is an opportunity not only to learn and to experiment and exchange on fair data practices, learn tools. OMISAR is going to be on the agenda, I know. But it's also more an opportunity to work together with image analysts at different facilities. And the idea is also to create links between people and bridge. So if you're interested, please submit your email address so we can inform you. But also, just in general, I can inform you in the newsletter. So if you get the Euro-BioImaging newsletter, you should find out when it's open. So yeah, joint lobbying, visibility for imaging. That's why it's important to be part of Euro-BioImaging. These European level funding opportunities, participation in EU projects. And of course, with Evolve, there's opportunities that are specifically available for node staff. And that brings me to community building. So I mentioned the website a couple of times, and I heard Caroline's going to revamp yours, and your ideas sound great. We were lucky to revamp our website in June of this year. So if you haven't visited our website for a while, I would invite you to go take a look. It has a new menu structure. We are able now to advertise jobs and training courses with the Microscopy DB, which is sort of a resource where we upload information about jobs that are open at our nodes and training, and they are shared with the international imaging community, because Microscopy DB is basically a network of partners who all share the same information. So think of this website as an opportunity to inform yourselves, but also to share your news with us, so we can share it with our community, which is international. So that's the website. Beyond that, we have expert groups. So I know you also have expert groups at France-BioImaging, and we don't want to compete with yours, but and a lot of France-BioImaging people are already involved, I believe. But yes, here's our expert groups. I run the communications expert group, and it would be really interesting to have more of you on board. We meet once a month. It's about an hour usually, and we discuss topics, exchange experience, and think about how to raise visibility for users in our work. So here's a QR code that you can scan in order to sign up for the expert groups. The virtual pub is one event that we run for the community. It takes place every Friday at 1 o'clock. It's an online lecture about either biological or biomedical imaging techniques, and sometimes image data analysis as well. If you can't make it on Friday afternoons, we do record these and we put them on our YouTube channel. So you can also check out the YouTube channel. But this is also, again, an opportunity for you to learn, but also an opportunity to present your work. So if you're working on a technology development, or some sort of interesting pipeline that you'd like to share at the virtual pub, let us know. We have a good attendance these days, usually between 40 and 60 people every Friday. So definitely it's an opportunity for you also to present. And here's the upcoming calendar. As you see, this Friday we have a special edition virtual pub, new model systems for biomedical research. And then the following Friday we'll have molecular imaging of cancer with SIRS nanoprobes, followed by the Tech Exchange. And the Tech Exchange is an online seminar from our industry board. And I was going to use that as a transition to this slide on industry. We're celebrating 10 years of collaboration with industry this year. Claudia Fander, she's our industry board coordinator, was meant to be here with us today, but she got stuck in the other side of in Karlsruhe, actually, because of the train system. But she did put together a really, really nice video series to talk about collaborating with industry. She interviewed a bunch of the people from our industry board, and there's a QR code if you're interested in finding out more there. She's also really developing this industry as user concept as well. So she's, it's really a shame she's not here to talk with you today. And really quickly, coffee break. I wanted to end on an international note. So looking towards global bioimaging, because as you know, you are also members of global bioimaging, right? Through Euro-BioImaging and also through your own involvement. So this community is really growing. Our globe is getting more purple every year. And the team at Global Bioimaging is also growing at the Euro-BioImaging BioHub, where I am. We're based in EMBL Heidelberg. The Global Bioimaging team members are also with us, and I think we gained at least 2 team members this year. So it's really exciting. They're doing a lot. One of the big projects they have right now is Imaging for All. And this is a funding opportunity for low and middle income country researchers. And it funds access to imaging facilities around the globe, including your imaging facility, right? It also funds job shadowing and training. So if you have amongst your collaborators somebody who's working in a low and middle income country and you're looking for a way to bring them to your facility, either to do a project, to get training, to do job shadowing, this is it. And this round closes on November 30th, but there will be also another round in 2025. So keep that in mind if you are working with people from low and middle income countries. The Global Bioimaging also runs what's called the Exchange of Experience Conference once a year. This year it was in Japan. Topic was image data. There were 300 participants coming from 47 countries. And what we were really proud of at Euro-BioImaging is that 5 Euro-BioImaging nodes were represented this year. And of course, there's France-BioImaging. So this is really fantastic. If you're interested, next year it takes place in Montreal. And that's in October, early October. There'll be information, more information coming out soon, but just to keep in mind. And then finally, Global Bioimaging also has its own international working groups. So this could be really interesting to you. It's complementary to the Euro-BioImaging ones in that it's more about core facility topics, like career topics and so on. But you're welcome to join these. And if you want to stay informed with Global Bioimaging, there's their website, and you can join their newsletter if you would like. And, oh, that's it. Take-home messages. So yes, by working together, we are increasing international user access, which is interesting projects for your facilities, right? And potential for collaboration. Also, you as members of France-BioImaging, you can benefit from some of the data services that your Euro-BioImaging Hub team is working on, and also benefit from this wider community, but also you're already involved also in Globius and stuff, but definitely there's a lot going on there. We're working to increase the visibility of imaging facilities, European level funding opportunities, and then all of these training and networking opportunities that are there through Evolve. So join our expert groups, check out the training courses and the job shadowing opportunities. And in order to stay in touch, you can follow us on so many social media right now because nobody really knows where to go, right? Yeah. And also there's the newsletter if you're really old-fashioned or have just given up on social media completely, which many people are doing. And you can reach out to me individually as well. Thank you very much for your attention. It was a real pleasure to talk to you.
Hi, everybody. I'm Etienne, Mission Officer for the Tech Transfer Call. It's my pleasure to chair this session, where you will see 7 selected talk from the 2 last call call in 2023 and 2024.
So it's my pleasure to present today the 3D lighted project. But first of all, I would like to thank the FBI on behalf of our consumption for its support, which made really possible to initiate this project. So our consortium consists of 4 partners from Toulouse Node. So the objective of this consortium is to develop a computational mesoscopic microphysiological imaging system. And so this project leverages our combined expertise in microphysiological imaging system with Laurent Malaquin at LAS and Audrey Ferrand at IRSD. We have expertise in numerical optimization with Florian Bugarin at Institut Clément Ader and advanced microscopy with me at Restore. So the 3D Lightis project is built on a patented MView platform, which is figure represented here. So it's a I'm going to say MPS for simplifying. So a microphysiological system, so MPS, which has been developed a few years ago by Laurent Malaquin and Audrey Ferrand. And so this system employs a molded hydrogel to mimic some 3D structure. So here you have a human colon structure represented here. And so it integrated some 3D channel for precise control of media and some glass cover slip as window to be compatible with standard microscopy. So here you have some example of human colon. So we can do confocal microscopy, but there are many challenges in imaging throughout this system, because we only have the surface of the reconstituted tissue. So here you have some examples. So, but the problem of this system is we would like to extend it to a different kind of reconstituted tissue or organoids, which measure several millimeters in size, so that exceed the depth of field and field of view of traditional microscope. So we are really limited. So, and we would like also to do long-term imaging for longitudinal analysis of these samples. So this results in a lot of challenge. So we have depth of field is too small. Field of view is limited. The resolution is low in these samples. And they are phototoxicity, so that avoid to follow the sample long term. And so moreover, we want to keep the sample sterile, and we want to image them many samples at once. So the 3D lighted project surpass this limitation by using an advanced imaging technique inspired by the work of Zhu and All. So they developed a computational miniature mesoscope for imaging neural activity in mice and correlate this activity to the behavioral studies. So their approach use a microlens array that allow to capture a highly encoded 2D imagery from an entire sample volume and in one shot. Okay, so this tailored microlens array extends the depth of field and the field of view of the imaging system and enable to capture a lot of integrated details. And then you have a custom reconstruction algorithm that allow to decode these 2D images and separating the depth information. Okay, and so we can get like this a 3D visualization with one 2D image take in single shot. So they have some impressive result, as you can see here. So they achieve a field of view of 7-8 millimeter with a depth of field of 1-2 millimeter and with very good resolution, axial and lateral resolution. So here you have the MembO concept, so which is based on this publication. So the key feature of this system is to integrate a microlens array and some 3D channel for light illumination within the MembO platform. So, thanks to France-BioImaging, we acquire a microlens array, and so here you have a microlens array. It's a 3x3 microlens array. And the LED are used for exciting the sample. And so we collect the emission fluorescence thanks to this MLA, and that capture the signal to a CMOS. And the target that we have for us, for this application in particular, is to attain a field of view of 5-8 millimeters, and a depth of field of around 1 millimeter, and with an isotropic resolution, axial and lateral resolution. So it's not high resolution, but a good resolution. And this will allow us to take the whole volume in one shot. So to do fast imaging. So, okay, and so for the design of this MembO devices, we employ an iterative design strategy that blends physics-based modeling and advanced algorithms development. So for optimization of optical component, we use ZMax. Again, thanks to France-BioImaging, we got this multi-physics platform, and so we can determine what are the critical imaging parameter, and optimize again the optical configuration. We use also we run some simulation with Jupyter notebooks in order to see how evolve the field of view and depth of field regarding the microlens array that we use, and the arrangement of a number of lenses, the spacing, the distance between the MLN and the CMOS, the distance between the MLN and the samples. And we were able to hear in last February, again, thanks to France-BioImaging. So as I said, it's really, this support really made us to initiate this project. And so it's a postdoc very skilled, so in theoretical and algorithm and physical modeling. And so it's leading the creation of a new and unified library for 3D reconstruction, which include some last development, very recent development in attention network for Fourier transform, universal PSF methods. So it's we think that the completion of this library will be okay in March, I hope. So we will be able to, after that, to have an iteration design strategy by linking the physical-based modeling with this 3D reconstruction algorithm. So this project is not only today. I'll talk about only the design of this device, but the project is more than that. So we have free work packages, because what we want to do once we have this design is to use some technology available at the LAS, which is selective glass etching, to do a monolithic glass microphysiological system integrating all the optics. So this cool, able to have some sterility and to manufacture this system quickly and fast. And also, we, as I mentioned already, we want to adapt this system to other kind of tissue and organoids. So we have a work package about organoid and reconstituted tissue culture in the EnView platform and MesenView platform. So, okay, I think I have finished. So if you have questions, so sorry. I apologize for my English, sorry, and my stress.
Okay, so I will show you the MAPS project. Stands for Multicolor Imaging and Absolute Positioning using planar all dielectric surface enhanced turf microscopy. So I guess all of you knows turf microscopy. A short introduction was this, right? Okay. So in turf microscopy, as you know, you move the angle until you reach the total reflection, and here you start to have an evanescent field that is enhanced compared to the long-range propagation field. But in fact, what people never take into account is that you have a given divergence of your beam when you do that in a microscope, and due to that divergence, in fact, you still have some propagative field within the sample, which ends up in a contrast that is not as good as what you could expect at the beginning. So one way to avoid that problem is to go further at different angles. But if you do that, then what you see is that you will have a decrease in the exaltation of the evanescent field, and you will have a lower contrast. So what we developed a couple of years ago is to find a way to restore this contrast by enhancing locally the evanescent field, thanks to some dielectric materials. Here is a cover slip, so the glass cover slip, classical glass cover slip, and on the other side you have these dielectric materials that enhance the field at an angle that we can choose. So why did we go for dielectrics? Because this technology is not new. People used to do that with metals previously. The big advantage of the dielectric is that, in fact, you can have the resonance at different angle and different wavelength. So you can choose a couple of angle and wavelengths depending on what you want to do. So you can achieve multicolor imaging. And the last layer of this multi-dielectric component is a SiOX layer, which is glass, in fact. So it's totally compatible with cells. So we did that a long time, well, a couple of years ago, sorry. And we already showed that experimentally we can achieve what we numerically predict. So here is the enhancement of fluorescence compared to so one is the far field fluorescence, okay? This is classical glass. When you reach the turf angle, you should expect to have a 4-time enhancement in the fluorescence. And thanks to our components, you can reach up to 7-time enhancement in the fluorescence at a chosen wavelength and a chosen angle that we can decide. So this is the calculation, and this is the experiment. And just to show that this works. So we say, okay, maybe we can use this component to try to be very precise in the Z direction and to have a precise positioning of the object we want to look at. So for this, we use the very simple principle that is the evanescent wave decrease exponentially with the depth, and this exponentially decrease also depend on the angle and the wavelength. Okay, and if you plot, for example, this I as a function of Z and theta over I as Z as 0, and as a function of the angle, this is the predicted depth of field that you will achieve. So what you see is that, of course, if you increase the angle, then you can look at objects that are closer to the surface. So the idea from here is that if you look at 2 different angles, you can make the ratio of these 2 different angles. And because this ratio is a ratio of 2 exponential, then you will have a precise localization. And you can see that this ratio will decrease linearly, approximately, as a function of Z. So you just have to know exactly what is the ratio of the intensity you have there. And you can already say what is the position of Z of your object. So for this, we develop a new dielectric material on the surface where we have not only 1 resonance, but we have 3 resonances on the surface. So these are the 3 numerically predicted resonances. And you can see that there is a resonance around 77, 1 at 73, and 1 at 66 degrees. And of course, this is the case where there is no divergence of the beam. The beam is perfectly propagating into the sample. But if you take into account the divergence, now the ratio becomes like this. Okay, you see that the divergence has a strong effect on the enhancement, but this is known. But nevertheless, you still can see that you have two peaks that will help you determine exactly at which angle you're looking at the intensity. So if you do that, you can already predict numerically that the ratio between these two peaks for an object that is at the same Z position will be equal to 1.4 approximately, meaning that if I observe this object using an angle of 77 degrees, the fluorescence will be 1.4 higher than if I observe the same object at 73 degrees. So this is the numerical calculation, and now this is the experiment. Of course, again, in the experiment, the divergence is not exactly what we put in the numerical system, because it's always very difficult to determine into the optical microscope. Nevertheless, if we perform exactly the same experiment, so we place an object at Z equals 0, we just scan our angles, and this is the profile we see, and now we see that these two ratio is approximately 1.2 times, okay? So based on this, we can now make a new cover slip where we will implement on top of it a step of 100 nanometer, which is made with a material that has the same refractive index than our biological object. And we put on the surface of this a lipid bilayer that is only 5 to 6 nanometer height or 8 nanometer height. So meaning that this is infinitely flat. So the Z position we're going to look is not the convolution of the field by the object, because the object is a kind of direct object, at least in the Z direction, okay? So this is the lipid bilayer. And now if we do that, we know already that if we look at the 0 position in our cover slip, then we have this profile. We can apply the following very simple ratio to predict what's going to happen if we look at 100 nanometer. So if you make this very simple calculation, 1.2 times approximately 0.8, you will end up in a ratio of these two peaks that should be only 1, okay? And this is experimentally what we observe. So we've made the proof of concept that we can determine precisely the Z position of an object just by looking at the ratio of these two lobes on the theta scanning over the sample. So all this has been done thanks to FBI. I will explain how it has been done, sorry. So FBI helped us to buy the CMOS cameras and one optical table, also to buy all the lipid beads, all the things I haven't shown. Of course, I show only the things that are working. And the cover slips production also from the Fresnel Institute. Buying also some hours to test the system on different microscopes, including the MRI facilities and the semi-pi facilities in Montpellier. MRI facility allowed us 15 meters square space to develop the project with a microscope that we built thanks to a Nikon TI PSF coupled to the latest TURF microscope of Abilite that allows the scanning of the theta very, very rapidly and to a very precise positioning. And of course, finally, our partners and us, IDs, know-how, human resource, and the cover slip design and manufacturers is made by Institut Fresnel. So finally, the timeline also, because I would have liked to show you much more results, but we were not that lucky. The grant started at that time, but before we got the Abilite dedicated microscope, even if we had access to other microscopes, scanning in the theta was not that easy. So it took a lot of development before having good results. And we have a PhD now starting working on that project, but unfortunately, because of Steve and blah, 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 he only came into the lab by October 2024, and now the project, at least by the FBI granting, is ending, but it's going on thanks to this CIFRE PhD with Abilite. And I think that's all. I did it very fast. So I want to thank all the people that have been involved in the two aspects. Thank you.
I'm going to present the TempFocage project. I'm working in the group of Laurent Bourdieu. So in IBANS at the Institute of Biology in École Normale Supérieure. So this presentation is about temporal focusing and custom access serial holography for 3D ultrafast optical functional activity recordings. So the 3D cache system was developed to acquire ultrafast optical recordings of the neuronal activity in 3D distributed neurons in the cortex of head-fixed mice. So the strategy that was used there was to modulate the spatial phase of every single pulse to be able to deflect the light from one neuron to another one successively. And this relies on a setup that looks like a 2-photon microscope, except that AODs, so the acousto-optic deflectors, are used to scan the beam. And these acousto-optic deflectors have 2 advantages. And the first is that they're able to go very fast because the acoustic wave settles quasi-instantaneously within the crystal. And the second advantage is that they can also act like spatial light modulators. Okay, but so the main point of that project, is that there are some fluctuations of the cell-tagged positions during the acquisition. And that could be mitigated by implementing light patterning, so using some grid patterns, as you can see here. And this way, all the artifacts could be almost like cancelled. But so the light patterning has another disadvantage, which is that it also there is also excitation out of the focal plane. So as you can see here, when we shift from a 1x1 grid to a 5x5 grid, we see that we have excitation out of the focus plane. And this creates from fluorescence coming from the neuropil out of the soma of the neurons. And therefore, we need to reduce the labeling in the tissue. So the FBI project, the aim of it was to improve the SNR in this system to be able to have better recordings and in more neurons. Okay. So for that, we developed, we used a temporal focusing that we tried to implement on the 3D cache system. So for a fluorescent signal, typically you see that it varies inversely to the pulse duration. And in the case of temporal focusing, so the pulse duration varies along the optical path with a minimal pulse duration exactly in the focal plane. Okay, but so it was successfully implemented for spatial light modulators, SLMs, but with AODs it's much more challenging because they introduce some angular dispersion, also some pulse front tilt, and there is also a normal dispersion with the separation in the time of the different components. So to get the best solution for us, we did some numerical study using some ray tracing while combining the acousto-optic spatial light modulator and the spatial temporal focusing. So the light goes through, so impinges onto a grating, then goes through a cylindrical lens and goes through the objective where it's focused. And we place the AOD at the back focal plane of the objective. And you see that along the y-axis, so all the spectral components propagate on distinct optical paths, but not on the x-axis where we perform actually the holography. So we multiplex the line that we created. And this simulation predicts that for a laser pulse at 920 nanometers with roughly 200 frames per second, we may expect to reduce the sectioning to almost 2 microns by actually, if you see, just before the AOD, we placed an AOM. And that is the key point. So a feature of the AOD is that it introduces some pulse front tilt. So one side of the beam just propagates is a bit arrives before the other side of the beam. And when we separate the colors, this translates into GDD, so meaning that the pulse is elongated. And you see that at the objective, so the pulse duration is quite large. But when we placed an AOM before the AOD, we can cancel that. So we can mitigate the effects, the drawbacks of the AOD. Okay, so the FEM2Cache project enabled us to build that setup and also to fund a postdoc. So you see that the light propagates, goes onto the diffraction grating through the AOM IOD, and at the end of the setup, so we placed an autocorrelator, the CARP system, and we moved the position of the CARP to do some measurements of the temporal focusing. Okay, so these are just preliminary results, and this project is still ongoing. So first, without any grating, we used only the AOD and the AOM, and varies the position of the AOM. And we can see that when changing the distance between the AOM and the AOD, we can reduce we can go back to the minimum pulse duration for the right distance between the AOM and the AOD. And when we implement temporal focusing, but this time first without any AOM and AOD, we were able to find this kind of variation of the pulse duration as a position along the optical axis. So these are only the first results that we got so far. And the next step will be to measure the pulse duration along the optical axis when having also the pair AOM and AOD, and to implement holography, and finally to see if we can indeed improve the SNR and and increase the density of the labels. So this is the team at the ENS. And so I thank you for all the events.
It will be a short talk, I think very short. Because I will just describe you we were funded by FBI. It was I don't remember the name. The development, l'appel d'offres, c'était le funding. The 2024 funding. I forgot the name. Development, no? Yes. Facility help for development, something like that. I'm sorry, I forgot. In fact, thanks to this funding, we were able to recruit one engineer for less than 1 year because academic is long. She came to us in April, I guess. So yeah, in fact, she really helped us in the everyday management of the facility, allowing to dedicate some time and to invest in some more particular way to make acquisition. And this is one example I will describe to you. There are a few more. And also, really, which is here, also did some of this kind of development for multispectral focal acquisition, for example. So smart microscopy is quite generic name. Even no one, everybody is not so okay with the definition. It's like a very enhanced automatic acquisition. And the idea is that we are trying to implement some steps where the microscope, the device, will take decision to what to do next, what will be the next step, like a human will do when you find a cell you want to analyze more precisely. You move the stage, you find the good one, you change the objective, you change the settings, and then you do the particular acquisition he wants to do. So the idea is to make it completely automatically we put the sample on the stage, one click, and it's done. Approximatively. It's it? Yes, that's it. So this is for one example of what we have to put in mind before scripting something. It's quite simple. Each step by itself is very simple. It's a very common problem we have doing the focusing creating presets for the microscope in order to have the nice images. Doing that independently, it's very easy to do. Doing it in one row under one interface and make it work, because it's not only scripting for image analysis, it's scripting that will drive the microscope. Sometimes there are some conflicts between what we think and what the device will do. Sometimes when it's simple, when it's complicated, the script is easy to elaborate in our head, and to make it work, we need to sweat a little. So what I will just finish with one example I did, because we did a few projects where we try to enhance ourselves doing fully automatic and close to smart microscopy. So I will explain to you. So what we do, we are close to the Nikon Society in Nantes. We are a center of excellence. So we have a lot of systems, and maybe some of you know that Nikon has developed the software inside their own software called NIS, plugin called Jobs, which is well done. It's like a new version of Metamorph, where you can script every function available in the microscope. You can add some JavaScript language, some Python language in order to make quite complicated analysis if you need. So you can create like different steps of driving the microscope, putting image analysis inside the microscope. Thanks to this analysis, will change the setting or not, or continue to screen or things like that. It's a step by step. So the idea here, for example, I will show you on the next slide, just to find, we have a multi-well plate where cells are in culture with a GFP positive, quite noisy, but we are trying to find a primary cilia, very specific small objects inside one per cell, very brilliant, very fluorescent, but quite small. It's like 1 micrometer, so we need some resolution. So we are doing that on a confocal microscope, and the idea is to screen multi-well plates, to find some cilia of interest, to retrieve their position, to do 3D stack along a few hours, then stop, moving to another position and doing it again and again in order to follow this with the confocal precision some quite rare events that became less and less rare a long time, because we need to do the last experiment that will last 5 days without losing the focus and the lasers and the stage, okay, and the computer and the server. So this is just I made a screen capture of what occurs, what it looks like. So this is the first step, classical. On the left, it's just the script that is appeared. So there is no need, for example, in the Nikon software to be good at Python or Java. Everything is done for a user-friendly interface. So here on the upright, it was all the dimension. It was where is it? Okay. Oh, you have the text on the slides. So that's why I did it. I learned a lot during the training group in order to do this kind of video, thanks to Fabrice. What I use, for example, to find you, maybe if I can switch back and then on, just try to, this one. Next. No, the step where the cilia were found by the software were done because I trained previously, because in Nikon software we also have access to AI training software that I trained myself on a fixed sample. So this is the segmentation. It's not easy to find. You have to agree that the noise is very noisy and the signal is not very brilliant, but it's good enough for the training to find the object. And after that, we are doing the whole process on one well. It's finished. The other well, like a classical screening content microscope. And the idea at the end is to have this kind of movie. It's a three-dimensional movie a long time. It's a long time. It's an overnight experiment. And this object lasts between 1 or 2 micrometers long. And we are trying to find this budding event, very small one. It is painful, but it works. And I am done. This is a team we have in the facility microbial here in Nantes. And the people involved in the grant was Aurélie Jousseau, which is here. So thanks a lot.
Stephen, it was an R&D project, and so merci. So FBI funding the high wing of CDD to help us on the facility, and so it gave me time to develop a new methodology on the facility, so the FIPSEM. So I will show that to you. Ouais, ça marche. So everything began in 2 years ago when we acquired a new microscope for the facility. So it's a focus ion beam combined with a scanning electron microscope. So there are several applications for this microscope. So I will just show you the application about volume acquisition, because it's the main application we have for this microscope. So the volume acquisition, first I wanted just to show all the project that has been initiated last year with this microscope, which is very new. Oh, je me trompe. Voilà. So we have first an ANR project that was funded before the microscope was installed about the celiogenesis in eukaryotic cells with our institute and also with the University of Lyon. Another project about the membrane remodeling during stress and development in several eukaryotic models. Another project about the cell wall formation in mycobacteria, a project about the secretory system of Chlamydomonas with another node of France-BioImaging, the University of Rouen, and another with the University of Leicester. Both of them was funding by Euro-BioImaging. Also, we have other project about infection of Listeria, endosome differentiation in melanocytes, and also 2 other projects about plants. So as you can see, FIPSEM is a pretty attractive methodology. So we have stuff, so that's why it was very important to be fast in the development about that. So all of that is 9 projects with 9 different laboratories, and 4 of them are outside of the region. So how it works? When you want to do FIPSEM in a volume acquisition with a FIPSEM, you have a resin block like for a transmission electron microscope, and you put the resin block in the microscope. So you can see here the resin with the sample embedded inside of it. If we see the block by the top face, we can decide that we will image this ROE, region of interest. We first deposit a little layer of platinum, then we make some marks that will be used for the autofocus and the tracking, and then we dig a cross section just below the volume that we want to image. And at the end, the video, no. Régie, can you put this video on, please? So this is the result, the final results, if it works. Just this image. You can see after, when we have dig with the cross section, with the FIPSEM, we will remove small slices of this place and make an image after every slice. Vous y arrivez ou? Non, c'est pas grave, no matter. You can imagine. We are supposed to see this cross section go deeper and deeper, and we can image all this square, all this volume. So here is a video that works. Non, elle a marché juste avant, c'est bon. So here is an example of a dataset acquired with the FIPSEM of HeLa cells, and it was to study the biogenesis of the lipid droplets in these cells. So the voxel size is around 15 nanometers in a 3 direction, and we can see at this resolution all the organelles in the cells. So the sample preparation for the FIPSEM is really close to the conventional sample preparation for the transmission electron microscopy. So we have a chemical fixation, then we make a post-fixation to have the contrast. This is the phase that can be really improved because you can add many metals to improve the contrast. Then we dehydrate, we put resin embedding, and we have a resin block that we can metallize and put in the microscope. The resin properties are also important to improve the milling condition. And here I just show you an example of some comparison of different protocols we did to try to improve the contrast in the FLIM. So these are the green steps are the steps that we had changed to make a comparison. And you can see that for all protocol, we add more and more metal in the sample. First, just osmium. In the second protocol, we put osmium and uranyl acetate. And in the third protocol, we put 2 layers of osmium, here, and here again osmium, and then uranyl, and then lead. Oh, je me trompe. And here is just a comparison of the images obtained with the 3 protocol, and you can see that the more metal you have in the sample, the more contrast you will have in the final image. So we continue to work on this improvement of protocol. First, we try to simplify because all these steps are very long to do and it's not very convenient. And also, uranyl acetate is more and more complicated to use, so we try to use some substitute to replace uranyl acetate. And also we work to change the fixation. So it's still in progress. So I have a little post-it on my desk with many tasks to do. First, as I told, we still work on the sample preparation and the acquisition, and we also work to develop protocols for cryofixation. So here is an example of an image. It's a very fresh result. It was acquired last week on the Chlamydomonas, and it's a cryofix sample, and we improved. So no, I didn't. Sophie Bernard from Rouen improved the protocol to have a better contrast. So it's still in progress, but it's pretty encouraging. We also try to develop a routine protocol for the volumic correlative light and electron microscopy to correlate fluorescence microscopy with the FLIM. And also hard work to do is to make the image analysis, and with a big step, which is segmentation of the data. So here are some examples. For example, here's the lipid droplets in the HeLa cells that I showed you just before. So they have both all been segmented to have a 3D reconstruction. Here it's an autophagic structure in C. elegans, and here is just some bacteria. And I want to thank, of course, France-BioImaging, because all this work is very time-consuming. And so thanks to France-BioImaging, we were able to hire Lydia Assistance. So Lydia and Cynthia worked hard on the electron microscopy to give me time to do the FLIM, so it was very helpful. And also, I thank my colleague from the photonic microscopy, and especially Valérie Nicolas, who is in charge to develop the volumic correlative microscopy. So she's very brave. And all of these people, because all these projects, it's very, very loud to do. It's a big work, and so it's possible only because they are all very implicated in the sample preparation and acquisition. And that's it.
Okay. So hi to everybody. So I'm Mathieu Fallet. I'm working on the Pixel platform in Marseille Lumini. So in CIML, Centre of Immunology of Marseille Lumini. And I will present you how to extend the number of colors usable in spectral confocal microscopy. That is a project that we develop with a researcher, Hugues Leloir, and with CDD Alexis Bonapi from France-BioImaging. So he has a 10-month contract, and he was a great person that worked on the platform and also helped a lot on this project. So. You probably know that there is a lot of system, hype-like systems that able to do more than 40 colors. But there is some limitation on this system. They are often wide field microscope, and also you work in 2D, and it's a very long time experiment, and it's quite destructive for the dyes. So there is, and maybe you don't need to make 40 colors on your microscope. In your project, we need maybe 15 to 20 colors. There is also some system from rare site Orion that make intermediate number of colors. So it's not hyperspectral, but we can say it's superspectral microscope. So we are in this range of not multispectral, not hyperspectral, but superspectral number of colors. For this project, we use a classical, I will say a classical, it's not a classical, but it's a confocal from Zeiss, the 980, with NER detectors. Okay. So in immunology, the purpose is to identify immune cells in tissue and also some structures in the tissue like blood vessels, lymphatics, or epithelium. So for this project, we need 15 to 20 colors. So yeah. So in 2018, we developed a panel that we make a NOT application with Zeiss from 9 to 10 fluorochromes in one shot, so in 1 second, that we present in MIFOBio at this time. And so with the near-infrared detectors, we can imagine to have 3 additional dyes because we can use three channel more, the channel 2 also, from Zeiss, from this microscope. There is some functionalities now in this microscope that enable to make 3D mosaic very well, like a little bit like a slide scanner. So for our project, it's very useful to have a very large statistics on a whole tissue. And what we want also is to quantify these different cell population and to look for cell-to-cell interaction in 3D. So here you can see a phagocyte that interacts with the 2 T cells. Okay. So what this work is still in progress. So what we want to do is to have 15 to 10 dyes. So the strategy we try is to make a sequential acquisition laser by laser and try to use large stock shift dyes in order to use the spectrum on the right of each laser, of course. And so by this way, using different fluorochromes that sometimes are used in cytometry, we are now at 13 dyes, which is not quite a lot, but we have a lot of place, so we can imagine going to go further. We also make a logical tree for a user to help user to construct their panel, depending of the signal brightness, antibody, etc. So it's quite useful for to build their panel. And so here you can see some images that we do with the collaboration of Hugues Loire, and you can see 3D reconstruction here from a crop. So you have 27 slices Z-stack, so you can have a very good 3D reconstruction for each interaction. And what we now do is to quantify these interactions with the help of Thomas Boudier in École Centrale Nice, with a Jupyter notebook, and that we count the interaction in this image in 3D, and then we randomize the lymphocyte, the T lymphocyte positions in 3D, and we look for the distribution of a random interaction versus the selective interactions, and in order to know if our interactions are just proximity or real contact. Yeah, you see a 3D reconstruction with 2 T lymphocytes, a phagocyte, and the proliferations cells in yellow, and with the part of contact. So it has been reconstructed with Imaris here. Oh, finally, so what we would like to do to be able to have a very good system. So as you see, DICE just add 2 infrared detectors, but it would be great to have an array of detectors that can go from 400 nanometers to 900 nanometers. That is existing in cytometry techniques already, in spectral stoichiometry. So we don't know if DICE have this, we would like to develop this part, but it would be great. Also, if we use like super continuum laser or additional laser in this near infrared part, we'll be able to use more dyes, more specifically. And in the software part, you have sometimes some problems. So a better algorithm for unmixing would be great. And of course, a dream will be to integrate the lifetime of fluorescence. That is will be interesting to make spectral lifetime. That is possible with the Leica system because they use a white light laser, but not in the DICE system. The excitation spectrum also could be interesting to use to help for unmix. And finally, what we could develop here in our project is to test new dyes in the near infrared range. So I will be interested by the roundtable on dyes, I think tomorrow, development, and to have different large stock shift dyes. So we will propose a training in 2025 on these techniques within CERN in Marseille, so you are welcome to participate. Thanks for your attention.
Thank you. Thank you for the opportunity and for the funding of France-BioImaging. Then today I present you a project about the development of FLIM-UV microscopy, optimized for living and nucleic acid imaging. Why imaging specific nucleic acid sequence, especially RNA? RNA is an intermediate between DNA and protein, but there are more activity in protein expression, isoform regulation, chaperone, signaling. All this process is involved during the development, cellular differentiation, or stress response. And a default in this activity give a potential disease. There are RNA is default is involved in many cancer and syndrome. And we work in the Faculty of Pharmacy, and many pharmaceutical companies work on with RNA as a therapeutic engine, siRNA, heptamer, mRNA, like for the vaccine. Then, as this importance, there are many tools to imagine live nucleic acid. There are 3 big steps. One strategy is to tag a specific sequence with a protein or complementary RNA, DNA fluorescence. Another strategy is to label directly the RNA or DNA with covalent labeling with a bright field, bright fluorescent, fluorophore. Or another strategy is to substitute one or more base by an analog, fluorescence analog, like there are many stuff. But the problematic of this approach is to maintain the activity in the same time to have enough signal. And then, since 10 years ago, the laboratory of Yves Mély and in collaboration with the ISACTOR lab in San Diego have studied the potential of cyanoguanosine. It's a perfect analog of the nucleic of the guanine, and they are also the advantage. They have less quenching, not many quenching when they are in the structure of nucleic acid like a double strand, but also a loop or in the quadruplex. by this potential, on another advantage that it's environmental sensitive, then the fluorescence is affected by the environment. Then the dye is used to follow, for example, interaction between DNA and chaperone methylation protein, like here with SRA, by evolution of the intensity, but also we are able to follow DNA annealing by a nucleocapsid protein. By this way, we follow the effect of the annealing on the lifetime of the dye. But one question is to know if this dye is suitable for cell imaging. Then for that, we have tested this tryanoganosine on the FLIM microscope, but the limitation of these dyes, the excitation is close to 350, and they have the brightness similar to the NADPH. However, the lifetime is longer, between 8 to 20 nanoseconds, compared to the autofluorescence of NADPH close to below 3 nanoseconds. Then we have do a preliminary test. Then we have used your own two-photon microscope with a pulse laser, with a long pass, and we put the tryanoganosine on the cell media, and we wait 30 minutes, and we collect FLIM image. Then here we have the FLIM image, and if we see the decay of fluorescence, then you have the short lifetime due to the NADPH autofluorescence on the long lifetime. But however, when we just do analysis, the majority of the signal come from the NADPH, then corresponding to this image. Then we tried the strategy to add a time gating. Then we exclude the first 8 nanoseconds of the signal, and by this way, we collect only the signal for the tryanoganosine. Then, and we are able to distinguish the tryanoganosine in the cytoplasm with a short lifetime around 10 nanoseconds, and a lifetime of tryanoganosine in the solution close to 20 nanoseconds. And by this result, we have obtained a finding about to develop a new system. Then we buy to a system optimized for imaging this tryanoganosine in the cell. Then it's close that we have seen before on the Rhône-Alpes node. It's a FLIM microscope based on the TIRF system to obtain a gentle excitation, and with a FLIM camera working in a TSPC mode. And for the excitation, we start to titan sapphire with a second harmonic generation by to obtain flexibility to are able to excite in 350, but also in for close to 500 for more classical dye. And yeah, and now the roadmap. Then we have obtained, we have ordered obtained the microscope on the optomechanics. Then you are in the lab, and to be sure, then with the funding of Ibiza on France-BioImaging, you have obtained money to buy the titan sapphire. Then this order is in November. Then they come in the lab in January. And when we after that we install all this system, and we have to still to buy the camera. Then but we prefer to have optimize the system before to test camera, because there are different strategies that the InScoper, but other techniques, and we want to see what is the best. And we have some project designed with this system, and we want to follow mRNA lipid nanoparticle for vaccine in live cell, and also nucleic evolution of acid nucleic in the nucleus. And yeah, and also I want to thank all the the member of the platform, the PIC Quest, all the member of the lab, and especially the team of Yves Mély, on the team of the platform of the UTBMC, the lab of San Diego for ISACTOR, and part of the modelization is done in Italy by the Mathieu Mori lab on the finding, especially France-BioImaging. Thank you.
Present the activities of the IPDM bioimage informatics node. Before starting, I would like to thank Jean-Christophe Olivier-Barin. He is not here, but he successfully headed this node since the creation of FBI in 2011. So he headed this. He was the first investigator of this node, and today we will present the current activities of this successful node. Right. He decided to nominate recently a new head and a co-head. So Jean-Yves and myself are now the new heads of the node, and for sure for a shorter time. For sure. So Jean-Yves cannot attend this meeting today, but probably some of you know him because he's the head of the FBIAS group or project. Right. Comment ça marche ça? Ah, par là. Ah, c'est l'autre petit. Ah. Tu as? Okay. Thank you. So to combine efficiently image data sets and image processing algorithm is generally necessary to develop performant, user-friendly software to meet and to satisfy multiple requests as reported on this slide. So this is a nightmare for many people of us, and so we develop a few solutions to address these issues. Right. So in this node, we mainly develop image processing algorithms, performance data management systems, data management plans, and recently we focus on mesocenters, data centers, and many of things related to data management and image processing. And of course, we have to adapt to new programming languages, Python, and so on, and new objects like Napari, who is now in our ecosystem. Right. So in 2020, the node was organized as follows. We have a core developer group composed of two teams, or three teams at the beginning, but two teams later, plus another additional teams. And we have the Jean-Yves created the image analysis hub, and we defined 10 associated research and development teams distributed in all nodes. But since the post-COVID period, this node has been seriously reshaped. And now we have a new project that I will show you in a few minutes. And this node needs to be all the time updated, especially now, because we have 4 new nodes. It means that you have new people who are involved in image processing and algorithm development. So we need to adapt to this situation. Right. So first, I would like to give you an overview of our activities, and the first step is to present the communities, because the IPDM group, who is a remote node, this node interacts with different communities. It interacts with the developer communities, people who develop proof of concept and image processing algorithms. The IPDM interact with the bioimage analyst group, who develop homemade solution with end users, and these solutions are generally integrated in research projects inside biology. They interact with the analysts in microscopy, who conduct activities in optics, in image acquisition and processing. And finally, the group interact with end user, and these end users are either biologists or scientists in chemistry or biophysics. Right. On the slide, we summarize our roadmap, and this roadmap is articulated around 4 practical projects. The first project is the FBI data project, headed by Perrine Pogilotto and Emmanuel Faure. This project helps at developing data management solutions that meet fair requests, data management plans, and while following the national roadmap that recommends to develop mesocenters and data centers at the metropole or region scale. In the FBIS projects, and aims at sharing expertise and methods between bioimage analysts within the infrastructure, so people are located in all nodes. And in the second part, in the bioimage IT project, we are currently developing fair middleware that can interact between image data and systems with image processing algorithm and pipelines developed with heterogeneous components, generally developed with different programming languages. And finally, I see software headed by a project headed by Jean-Christophe Olivier-Marin, started maybe more than 10 years ago now, I guess. The aim of this project is to develop a user-friendly solution for end users. Okay, so to give you more details about these 4 projects, the best things to do is probably to invite the coordinators to come on stage, and the first speaker will be Perrine, and Emmanuel will give you more information about this project.
Thank you. So thanks, Charles. We're going to be very quick. So Charles said what was the data paradigm that we were facing. So basically data deluge. We want to be and to help open science, and we want to help transition to data center, mesocenters. And for this, just something, we want to facilitate the life of staff in light and electron microscopy facilities. And that's the kind of tools that we are developing. So both an infrastructure as a service, which is, for example, using Homero, but Homero is just an interface, and we are not developing a new tool. It's really a full system where we try to limitate and to manage to mutualize the maintenance and the deployment at the national level in every node. So that's the important point. And this also allowing to organize your data following some recommendations which are at the international level, in order to then deposit your data on public archives. And this is basically something that was presented also by Marianna. There is this archive that you can deposit, so we are not going to create a new repository. We are helping to transition and to deposit data on this repository. And of course, I was talking about mesocenters. The idea, and that would be the goal for next year, is to give access to the computational resource, because there is more and more data, bigger data, and more data to process, and more deep learning algorithms that you want to use or to train yourself. So the idea is really to facilitate the access to these resources. just some update about the team. So everyone has a particular role. So these people are either 100% dedicated, either with a small amount dedicated to this project. And that's also people you can maybe meet and contact. So maybe they can just raise the hand so you can see who they are here. Yes, thanks. And I don't know if you have time to see them. And also recently we asked in every node to have some people dedicated to help us. And this is our data referent. And maybe they can raise the hand as well. So thanks also to the, they are not all here, but there is about 2 to 4 people in every node, which has a mission to help us also to disseminate and to install and to make some local contact with the deployment which is coming. So just also maybe quickly, we are doing this not alone. We are communicating also with other countries, other big projects and everything. So we really try to create together at the international level some standard and some way to process and to deal with our data. I don't know, Emmanuel, if you want to add something?
Yeah, it was very great already. Yeah, we just asked the data referent, and really thanks to them because we asked them a lot of things, and they are really important for us because they make the relation between the platforms and the national infrastructures. And we realized that we cannot do it by ourselves, so thanks for all the community for that. So we asked them to see if they need what we call a server tampon, which is a buffer which will be very helpful to transfer the data to the base centers. And we just bought 11 different servers, which cost a lot, and you should receive it by the end of the year. If it's not the case, send us an email, because otherwise it can be complicated. And this is the first step of the deployment, and we hope that by the end of the next year, we will have a great solution that will be deployed maybe in most of the nodes that require them, and maybe in all of them if it's successful. So we will see that.
So Charles, back, or maybe I should invite Anne-Sophie in the name of, on behalf of Charles. Yeah.
Anne-Sophie message because Jean-Yves is not there, but yes. Anne-Sophie is there. We are
so yeah, thank you. So I'm talking for Jean-Yves and myself. So about FBS, which is the group of analysts of FBI. So this is a group we've created really because sometimes analysts are isolated either in teams or in microscopy teams. And the idea was really to create a professional community that includes all the willing analysts in FBI, with really the goal to improve technically and scientifically. Yeah, I'm trying very hard. Yeah, so this is, I mean, some of the people are here also. So thank you for those that are here and for everybody that is participating like a lot in this network. So the first step, as I told you, was really to try to improve scientifically and technically, but now we are really trying to also help all the users community, the FBI users community. And for that, we are doing 2 specific things that I want to present briefly. First, this is the open desk. So maybe you've seen the advertisement by Caroline. So do not hesitate to transfer to your users or to come yourself if you need some help in image analysis. So this is a session of 1 hour where we really focus on the problem of one user. This is free for every user in France-BioImaging. And the next session will be in January. Do not hesitate to tell us if you don't receive them and if you want more. This is really thanks to Caroline. So that's it. This is something that is very positive for users, for analysts, and for the community. So we are very happy. But of course, we know that sometimes 1 hour is not enough for solving an image analysis problem. So the idea now is to also be able to take some collaborative project. And this is something that is really doable thanks to the support of FBI, because we have two short-term contracts that are funded by FBI really in this objective. One is in Curie, one is in Pasteur, which means that this year we've started 8 collaborative projects. I don't want to go into details in all of these projects, but the idea with this slide is to show you that we are helping on projects that are maybe not really what we are doing first, that is fluorescence microscopy. I think it was a movie here, but I don't think it will be shown, but it's like tracking of fish over there. Over there, it's electron microscopy. And in the bottom, sorry, it's also to show you that with some annotated data, we can help you also to make some deep learning algorithm. And so this is really, we think, a need, especially for a facility where there is not any analysts. So do not hesitate to contact us if you want, if you need, or your user needs some help on image analysis, because we are taking some projects, and this is really why we are here. Thank you to Euro-BioImaging, which with which we are sharing, I mean, not sharing, they are like our platform for applying for project. And maybe you've seen that, but we've published a preprint about our initiative, so we are also very happy about that.
I just have a comment on the EPDM node, if you mind, Charles. This is a very different node because it's not organized by facilities and engineers, etc. It's organized only with R&D team, with very strong overbooked PI. And I would like to say that it's not very easy to structure this EPDM node. So please, Charles, stay as long as you can. We need you for that.
Thank you, Emmanuel. I will try to do the effort. Okay. So I'm not the coordinator of IC, but I would like to say a few words about the software developed 10 years ago now by Jean-Christophe Olivier-Marin. And the current solution can be very helpful to manipulate, visualize multidimensional data. And you can create pipelines and so on. And it was, for the time being, it was developed was in Java language. By in the future, probably very soon, or next year, I hope, a new version of the software will be proposed to the community. It will integrate Python plugins and probably machine learning components. So you will be will have the opportunity to create new pipelines with machine learning based segmentation tools, I guess. Right? And so, and to finish, a few words about BioImage IT. Arthur Masson and myself are the coordinator of this project. It was first initiated by Jean-Saint Lemero, who is in the back here, and Sylvain Prigent a few years ago. And this software is a middleware. It means a fair middleware. It means that it is very helpful to connect data management system to image processing, algorithm and pipelines. It can collect metadata, and the metadata can be saved in the data management system. And the advantage is that you save storage because you don't need to move the data. The data are located, for instance, in the future mesocenters, and the processing will be run on computing facilities in this mesocenter. So Arthur Masson, to finish this session, has a short 2 minutes for 7 slides. Good luck.
All right. Hello, everybody. That'll be hard to make it in 2 minutes, but yeah, I wanted to create a small demo to present a small demo, but in the end, I'll show you a few slides. Hopefully, it will be faster. I don't know, really. BioImage IT is really a workflow management system, and it's pretty standard in this way. It's an interface that enables to create workflows. And so here you can see that you have a toolbox where you can pick some tools to list files or take them from a database and then process them, and then you can create a whole graph like that for your processing. And the data flows from node to node, and you can see here it populates this table here, where you have previews of the image, the processed images. Here it's an example where we begin with those images which are on one side tau protein images, and on the other side microtubules. And we want to study the interactions between the two. So the first node here splits the image in two, and you can see that there are two columns now in the table, one for the tau proteins and the other for the microtubules. And then the graph has two branches, one for the tau proteins, the other for the empty images. And in the end, after having detected and tracked those particles or objects, we want to merge those information and analyze it, and then we can actually study the, or have some quantification of the interaction of the tau proteins and the microtubules. I'm gonna show you a very quickly in 1 minute now another example of workflow. It's a workflow to train an exocytosis event detection model. So I skipped images about exocytosis events. I guess you know them more than me, but basically we want the model to predict segmentation maps with annotation, exocytosis events here and bright spots which are not exocytosis events in red. And so for that, we have the expert annotations and movies at the beginning, and we detect all the bright spots with this node here, and we convert the annotations to segmentation maps with this node, and this node here will merge both information. And you can see that on this table we see, I don't know if you see it very well, but the idea is that we merge all this information and feed it to the training node, which trained the model to detect exocytosis event. So yeah, that was a very brief introduction to bioimage IT. And yeah, if you want to talk more about that, I'm here, and I'll be happy to talk with you. Thank you.
Right. So to conclude, a final slide. So just to want to mention that these are different groups interact. So there are many meetings for many. There were 2 meetings in for the time being, and another between the FBI Point Data group and the FPS group. And next week we plan to create a new group. I selected the name FBI AI instead of developer, because developer is not clear for me. So it could be image analysis and artificial intelligence group. In Pasteur, the idea is to write a roadmap. And in this roadmap, we plan to gather people from the different groups, bioimage analysts and developers. And the idea is to probably to select the best algorithm, the best performant algorithm, the most popular algorithm that you can find in any node. And this popular algorithm could be shared with the other nodes. But it's a general amount of work to integrate a very good algorithm in a software, and the software to be shared with people. So we have to select a few strategic algorithms which are developed in our teams or in the world because they are popular, and to share this, all these best algorithms with all the community if possible. That's the idea. Right, and probably we had a larger EPDM group meeting in next year. That's the idea. So EPDM needs you. We need your contributions to make a PyDM performant and unprecedented research instrument for mutual benefit for all stakeholders. Thank you very much for your attention.
Hi everyone, I'm Doran Kaufman, or also the one who spam you to get much images. And today I will present France-BioImaging challenges. I'm part of a team with Emmanuel Faure and Guillaume Guy, with the advice of Edouard Bertrand, Thomas Walter from the EPDM which present earlier, Christophe Zimmer, Anne-Sophie Massé, Thierry Pécaud, and Stéphane Rigaud. So a challenge is like a competition, a machine learning competition. And why France-BioImaging organizing challenges? Because it's a structuring role but all across the France with much more than 20 facilities. Which help a lot to get a lot of images and to create open source databases and bring method bags, deep learning method bags to biologists at the end. So the aim is to create one challenge by year to offer useful tools for biologists after that. So in 2024, we made the Light My Cells challenge. The goal is simply to recover sharp fluorescence images by computer from transmitted light images. So, in other words, we asked to biologists to acquire at the same time, the transmitted light images and the associated fluorescence images for specific organelles. And for participants, the task was to, from only the transmitted light images, to predict with deep learning models these fluorescence images. And then we, thanks to the acquisition protocol, we have no manual annotation, and this is a task called image to image. Hop. So the timeline was very short, about 10 months, and thanks to the work of data contributors and the participants in very short time, we succeed to present the results at ISB in Athens in June. And it was a success. So here you can see the high variability of all the images, and we will publish a paper of all the data with all the contributors as a co-author in BioImage archive soon. So this is an example for the heterogeneity and the variability of the database, because it's about 57,000 images totally, and this is thanks to the all France-BioImaging nodes and all data contributors. Here you can see the database is very unbalanced, because we have 30 different acquisition protocols, or what we call a study. And for example, in the 25 study, you have a much more images, and as well for organelles, because there are much more nucleus and mitochondria than the other one. I'm fast, I'm sorry. So now I will just present the results. So we had 11 participants from all across the world, as you can see here. And for a first challenge organized by France-BioImaging, this is a very great number. And here you can see that the first one stand out from the others. And thanks to FBS, we will integrate the first 3 deep learning models into bioimage model zoo or deep imagery to bring methods back to biologists, as I've said before, for the motivations. So now, thanks to, I will just show you a few images. So this is the transmitted light inputs for all the organelles. And here, the ground truth, so the acquired data. And here, there are predictions of what we asked the tasks. So here, for nucleus and mitochondria, this is very nice. And for tubulin and actin, this is much more uncertain, as you can see here, because there are some things here, but yeah, this is discutable. And thanks to France-BioImaging, today we have the winner of the challenge, which was invited from Stanford to present the hair model. And please, Trang Li, welcome. Yes.
And then this.
And here to follow the next slide.
Okay, so that's two, I think. Yeah, thanks. So thanks for the kind introduction. Yeah, this is the first time I saw the makeup change, so I single-handedly bring down the height of all the speaker. Yeah, so Dorian already talked about the challenge setup, so I would like to offer my perspective as a participant. So I joined the challenge for around 2 months, so March and April this year, basically. And the task is straightforward. It's basically, can I go back? Oh, here. An image-to-image translation test, where given a bright field or any kind of transmitted light images, you are asked to predict 4 channels for every field of view. And there's a lot of obvious reason why we want to go label-free. Besides the reduced cytotoxicity and other reason, we can free up some fluorescent channels to pursue other targets. And also we can go to live cell imaging direction, where actually you can gather way more temporal information of the cell state that might be arguably much more deterministic of the system that we are studying. This one. So this task is actually not new. There has been efforts in paper, at least in the last 6, I think 10 years, trying to virtual stain from transmitted light images. But I think that this challenge still offers some novelty in the sense that this is maybe the most heterogeneous data set with gathering like 30 different studies and different magnification, depth of focus, etc., different cell type and morphologies. So because of this relatively large and diverse data set, there's offer a chance to generalize solution. So from the distribution of the data, training data set that were offered to us in log scale, you can see obviously that actin is 1/10 of the data for nucleus, which means that you have very much reduced capacity to model anything for actin. So there's a great class imbalance. And you can see here also that there are different combinations for each field of view or each study in specific, which mean that there are many incomplete organelle to organelle and organelle to transmitted light joint distribution to model. But according to, well, through my other PhD kind of studies, we learned that organelle to organelle relationship are quite robust within unperturbed population. So I wanted to investigate that can these missing joint distribution be modeled based on this very incomplete like joint distribution sets. So that brings me to my failed attempt, actually. That basically the idea is that I embedded the transmitted light to a latent vector, and through the and also do the same for the organelle channel, and through the diffusion process and organelle token conditioning generation, so reverse diffusion with token conditioning. I learned the mapping between the transmitted light image and the organelle distribution. And actually, as a preface, is not performing that well. It's actually the model failed to interpolate beyond the channel combination that is provided in the training set. So we lack enough data for this task in this challenge. However, this approach actually worked on another data set with complete joint distribution. And yeah, please feel free to ask me about it later if you're interested. So with time was running out, I default to a much simpler solution, which is one model for each organelle, so an organelle-specific VQ GAN. So it's basically an autoencoder with an encoder, and a decoder in this case acted as a generator that learned the mapping between a transmitted light and then the organelle of interest, and then a discriminator here that is forcing the generator to generate a more perceptually realistic image. And then we also have a quantizer in the middle that map the continuous embedding to a discrete one. And then the model size end up to be around 50 million parameter, and this is considered right now relatively light for deep learning. These models have become so large these days. Yeah, and this is what I have in my validation set. You can see that for most of the combination that I see, when I split like random validation and training, then my output looks pretty much close to the ground truth. So we were able to model most of the combination between transmitted line modality and channel, organelle channel. This one. So the conclusion is for modeling is that a simpler method actually works better in this setup. And I learned that modeling multi-organelle in this case require a lot more joint distribution information, and latent diffusion is very data hungry. And also when training the VQ GAN, I noticed that like the organelle with lower sample will require much more training tips and tricks than those with sufficient sample. Then you just let it run, basically. And then, yeah, scientifically, maybe we establish the current performance of the label-free model on these 4 organelle channel. And there's actually one question that I want to ask you as like experimentalists, biologists. At what point, like what kind of confirmation or confidence do you have to use this model? So when do you use this model, and how do you use the model? How do you imagine incorporating this actually in your research? Yeah, so I look forward to any discussion today or tomorrow about these. Thank you.
Thank you. Yeah, sorry. I will be quick. This is France-BioImaging annual meeting. So I'm announcing the next challenge, which will be fuse my cells. Very original. And the aim is to recover a fused 3D image from a single or dual available 3D multi-view images. Yes, this is very understandable. So simply, Multi-view light sheets this is a new kind of sample. So you have a sample and you can make four views of this sample with this multi-view microscope. And thanks to algorithm, we can fuse as an isotropic image these angles to get a very nice image. And so the task is from only one or both views, or one or two, to predict with AA the fused image. So to precise about fusion, here we have the four views, and thanks to Grégoire Malandin, which work at INRIA, we will use Aztec algorithm to make the fusion. And for example, here this is a Drosophila embryo, and you can gain this part with fusion. Hop. So the task for the participant, the future participant, will be to predict for only one or two views the fusion, and we will evaluate at the first time the pixels at the pixel level, and after for the usability for biologists, we will evaluate on the segmentation with cell pose simply. So the timeline is again very short, very short. So here we are in the data preparation, and this is thanks to all the data contributors. Thank you very much. Some of them are here maybe. And I will just finish about making a big thanks about the whole person who contribute to the Light Myself Challenge and the all data contributors. This is a big success, so thank you very much. And thank you for your attention.
If you have a light sheet microscope, please, you can do, it's still time to do some images. I know that Dorian already sent thousands of emails, but still time, you can do it. Okay, thanks you. And I would just like to thank Edouard, because when I asked him what he's going to do after leaving the direction of the FBI, he said, well, I'm not leaving, I want to stay in the FBI challenge. So thanks Edouard for that, he supports us a lot for this organization. Thank you.
Okay. Yeah, thanks a lot for the invitation. And actually, when I made the talk, I thought, so you invited me to talk about German bioimaging, but I think this is not fair, because in the end, I am having so many hats on, and also, if I'm here in Strasbourg, I think I have to talk a little bit about the sleeping thing, the microscopy and image analysis platform, which actually has also some members. Has also some members from Strasbourg and Mulhouse. So let's start with the MIAB network. I will make it very quick. So it was founded in 2016 with help of a grant from the German Research Foundation. And mostly it was a Freiburg network, but from the beginning on in the grant application, I decided that I have to include my neighbors on the other side of the Rhine. Actually, yeah, it's always on the other side of the Rhine. And so in Basel, Mulhouse, and so on. So in the end, that is a local network, Upper Rhine Valley, I would name it. And it was quite active after it was founded. And then in 2020, it fell asleep completely. Several reasons for that. First, the funding ended, and the university, which had promised to continue giving money, neglected to give it. And also then there was COVID. So that's two reasons. Very quickly, so in Freiburg, we have a bunch of imaging facilities, light microscopy facilities, as well as EM labs. And we are all together in the MIAB network, and we did during the time, yeah, we have a bunch of instruments. I think that's boring because all of you have instruments. And what was maybe very interesting for MIAB, we did many workshops because that was also the money for. So in the end, we had for our workshops more than 1,000 attendees, and they were coming actually from different places in Freiburg, but also from the surrounding. So we had at least 20 participants coming over the Rhine, and we had also people coming really from far away places because some of the workshops, I think they were quite interesting about macro programming for different software packages, and so it was a very nice thing, but it was not funded further. So that's the reason why it was sleeping. And I'm also a founder of German bioimaging, actually. So that started first not as a real Verein, as we name it in Germany. It was, again, a funding from the German Research Foundation. And then in 2017, we made something out of this, a real society. And I was one of the co-founders. And until 2023, I was in the steering board. And then actually, I have so much to do. I decided actually the young people have to start working in German bioimaging. So I'm still doing a lot in German bioimaging, as you will see, the trends in microscopy, for example. And the German bioimaging network consists currently of 52 imaging core facilities. And if you calculate with a mean value of around 200 people, it's, I think, 10,000 users approximately. We have currently 200 personnel members, and 18 companies are part of the network. So this means they help us to keep German bioimaging alive because we have no other funding anymore. But I think we are quite active. This is here the steering board, the current one, and Steffi is currently leading together with Hella, and then you know maybe some of them. And there is the image missing. So, and you see, I would be clearly the oldest guy if I would have stayed. And I think it was a good decision to do it. And Elisa, who was the co-founder with me, Elisa May, she also stepped back. So, because we are so successful, even without having funding from any body, we are able actually to have a full-time position, a managing director, a project manager. This is also now full-time person. And then we have, this is for the accounting, and we were able actually to hire Josh Moore, who many of you know from the name, I think. So he's connected heavily with the OME name. And we also are currently housing Christa Walter, who is actually the project manager of GloBias, which was recently officially founded. And why is GloBias together with German bioimaging? Because we are able actually to get funding from other sources, like in this case from CZI. In Germany, a university will not take money from CZI. So you have to find someone who can manage that, and we do that. And the advantage for us, we are getting the overhead. And from that, we can do more work. So in German bioimaging, we have different teams. The quality team, I'm working together with Hella Hartmann there, and we have some other ones. And I think the interesting ones for you are for sure the quality and the training and knowledge transfer, because there we work also heavily together. And we have some specialized groups about intravital microscopy and fluorescence lifetime imaging, and they make their own conferences within Germany, usually every year. So some things which were organized by German bioimaging and which you might know, and we welcome actually people from everywhere in the world. So we have the core facility leadership and management course. I think that was running this year for the, I think the 10th time or something like that. So we made it together with HFP, and it's quite interesting because it's a very specialized course, really for core facility managers. And it was adapted, or I can say it also a little bit bad, like the Euro-BioImaging, actually they steal the idea somehow, and they are selling also a course which is more or less based on what we invented. But that doesn't matter because it means it's popular. So we do job shadowing, and this we also do since more than 10 years. This means you can go to different labs and learn techniques or just learn how a core facility in another place is working. And we also have, if we have local courses, we allow that there is a one place for Gerbi. This means people can join a course from somewhere else, even if it's a closed course for a certain core facility, they have a free place from someone from the outside. One of the latest things which we did was we developed together with Fischer Technik. I have no idea if this is also known, this company in France. So they make actually toys, advanced toys, I would name it. And we came together with this company to make an optics kit. And this optics kit, actually, it's now available. And we have, within German bioimaging, we have 80 of these kits. And we can send them around for courses, students. And I think if France-BioImaging would ask, then we would also send this out for sure. We send this out in a package of 10, so that you can, for example, have courses where you teach 20 people, and there's a booklet about what you can build there. So it's starting from very simple optics up to, I would say, real microscopy things, pinhole things. You can do really a lot. There's a light source with it, and we will present this also, and that will be the next one here, again in the Trends in Microscopy, which is our biannual course, or not course, I would name it. It's a small MIFO-Bio, because we were stealing from you. So I think I was with Elisa around 6 or 7 years ago. We were in Arcachon, and we looked how France-BioImaging and the whole, I should not say France-BioImaging because I think that's wrong. The MIFO-Bio is organized from many groups in France. But we looked how you do it, and because we wanted to do something in that direction. So Trends in Microscopy is now running for the 3rd time. We found a very nice location, which is in the Schwäbische Alb. So that's in the middle of Norway. And Jérôme has been there, I think, 2 times already. And the reason why we do it in this location is no one can escape. Yeah, so there is nothing around. And it's a very intense week. I think it's coming to the intensity of the MIFO-Bio at some point. And we are now there with 63 hands-on workshops, and more or less it's already booked out, even if we did not make it really officially. So we decided we need 25 more places, so they will be announced soon so that people can register. And this year we have France as a partner country. So there will be 2 speakers actually here on this slide. There is only 1 speaker who was selected, I think, again by the France community. So we suggested we want to have some speakers, and then there was some discussion, I think, within your community, and then you presented us Sergei, and I think there is another person, the name I forgot, sorry. Because it was just recently presented, this name, I think a week ago or something like that. So, and we have special conditions, so I think all the people from France who will do workshops there, they will be invited, so we have money for that. And then we also reserved, I think, 5 places where people from France can register to attend the TIM meeting. So very quickly, why is German bioimaging, I would name it not rich, but so successful? Just because we are able to do with the people who are connected with German bioimaging to apply for grants. And the biggest one you see here, this is the NFDI for bioimage, which is the National Research Data Infrastructure for Bioimage. And actually, this is part of a huge funding scheme from the German Research Foundation. And I think it's 23 projects. NFDI is running for 6 years. And it's around, I think it's 8 million or something like that for this time. A lot of positions. And we have other things like this one here, the LEAP, and Josh Moore got another one. He's part of the founding guide. So there's money coming in, and from the overhead, we are able actually to pay the project managers and other things. Yeah, Robert Hase also had this Neubias grant. Okay, so just some examples where German bioimaging is heavily involved. One is the OME SAR. This is again pushed by Josh Moore a lot, and many people worldwide are working on that. So to generate, I would say, a new idea of a data format. So NFDI, I will just jump over this more or less. So it's 26 consortia, and NFDI is one of these. There is, for example, another one which is named NFDI for Plant, and they are all across Germany. NFDI for bioimaging has 4 working groups, and you see some of the faces show up again because they are all heavily connected to German bioimaging, and German bioimaging is part of this grant application. So we also get money via this way. And as you see, University of Freiburg is also part of this network. And now to the last thing. So the QUARE-BLIMI initiative, Quality Assessment and Reproducibility for Instruments and Images in Light Microscopy. That was such a long name that this was the only way to get rid of reading all this. So actually, this is a very old idea of mine, which I had together with Ute Resch-Gänger 20 years ago. And we developed this further, and I think a big developer of this idea is also the RTMFM group here in France. And I have many friends in there. But also some of the MIA people in Basel, they are part of this idea. So it's about improving the quality of light microscopy and also improving what you report about light microscopy. And in 2016, actually, I joined ISO. And ISO, many of you maybe have never heard about, or you know there's ISO, but you have no idea that it is working in the field of microscopy. So we brought out actually an ISO norm about confocal microscopy, which is mostly about quality control, but it does not tell you how you have to do things. So it defines standards, but it does not tell anything about the methods. So that is the reason why Bioimaging UK and also some other people you see here, Orestes and Alex and Glyn, they are from the UK. I'm part of this, and Laurent from Basel. So we wrote something, and then we saw this is so complicated, we have to make it better. And that's the reason why during Corona, luckily we had time to talk with each other over large distances. So we had a first meeting with 50 attendees, and now we are, actually this is not the latest number, we are 640 people worldwide working on quality assessment and quality control. And when you look here, maybe I jump further. So what are our major topics? So we want, first of all, talk and find and agreeing on a common language for the definition of terms describing microscopy, add-on equipment, and quality control and quality assessment. And then we have to, again, define and agree on common protocols for the measurements, and also we have to agree on the tools which we have to use. And then, if we do these measurements, we have to agree on a common storage format. So this means, currently you all know there's bioformat, and bioformats is there, not only of the file formats, because they are different, but also the naming within the file formats is completely different. So it might be Zeiss is calling the objective, and Leica names it within the file lens. Yeah, so that is stupid in the end, and we have to solve this problem. And you will see, I think we are on a very good way. So in the end, when we have agreed on all this with all these companies, because all of these company logos which you see here, they send members into QuaRep, and they take actively part of this initiative. And then we have also the standardization organizations. So there are national ones like DIN or the NIST or the AST, that's Japan, or this is the UK. But then you have ISO, which is actually collecting all these national within one body. So the stakeholders, they are researchers, light microscopists from core facilities, and all these networks, and the standardization organizations, and we also have publishers in there. So they are mostly observers, so they just listen. And we have also the funding organizations in there. We have 14 working groups, so one is missing because we decided that we don't need this anymore. And the first 6 are working practically. So they are really doing measurements. Then the metadata, this is the most complicated group because it has to integrate, and it also has to take care that we are not producing again the same what we have now, that everybody is speaking a different language. So we have to align each other. And we do that with the help of the NBOQ QuaRep LIMI model. And we also, because we are so many people, in the last half year, we tried to organize ourselves. So we have now a steering committee, an executive council, and we have an editorial review board, which actually is checking the output. So we want to keep a very high quality. So therefore, we decided no group can publish anything before we have seen it in the editorial review board. That helps, I think, to keep the quality. And because when you have 640 people, there will be not always just everything fine. So there will be conflicts, and we decided we need an ombuds board. And so if there is a conflict which cannot be solved within a working group, then it's transferred to this group, and they try to fix it. So we have a cloud server. We work on many different sites. So first of all, look at the website. There you can find a lot of information. We produce movies which are on a YouTube channel. We write protocols, and they are on protocols.io. We publish it there. We write a lot of macros to automatize quality control, because in the end, the baddest or the worst person, the worst player in the team of quality control is the human being. Yeah. So when you send someone doing measurements on the microscope and you let them do 5 times the same thing, 5 different persons, 5 different days, and then you see what is the result, you will see humans have a huge influence on the results. But that is something you don't like, so quality control has to be automatic. So you put a sample on the microscope, you have a macro, it's running, and then you have the result. Also quality control, no one wants it. It's boring, it's time consuming, you have to collect the data and make it present it in a nice way and easy way. So we have to make it automatic, otherwise it will not work. So we also work with Airtable. Currently we have no money for that because Quareb has no funding at all. So we try to get the money from whatever sources. Very often it's just ourselves or Freiburg. I misuse some of the grants which I have for helping. And Airtable is the idea, if you do measurements, you load it up into the cloud and then everybody can look at it. So how we used it, for example, for power measurements was uploading hundreds of power measurements from different instruments. So in the end, for example, you do a measurement, then you have no idea. Is this good, bad? What does it mean? But when you look, there were maybe 50 measurements already done with, say, an LSM 900 with whatever laser, and then you compare your measurement with what is in the database, then you can see, oh, I'm in the mean, or I'm on the left or on the right side of the Gaussian distribution. So this helps a lot also to define what France RTMFF wanted to do with the paper published by Tomasz and Orestes, is they wanted to have it simple like a traffic light, green, yellow and red. I think we are not sure if this can be so easy. We have to see, because we still have to define the traffic light. Yeah, and for that you need enough data. And currently I think we are maybe having not enough data. Okay, so social media we are using, protocols.io I mentioned, and I think it's a success story because we published already, I think now 6 or 7 papers in Nature Methods, and they are cited like hell. And the last paper down here, that actually they applied this working group 12, they applied actually with this topic, which is actually a checklist how you have to publish your images and how you should report about that. And that checklist can be downloaded, and they send it in to the Einstein Foundation. That was just coming out this Monday, and they won actually the Einstein Early Career Award exactly with this workgroup 12 Quareb thing. And the nice thing, they got 100,000 euro for that. So it's a, I would say, high-ranking award, and I hope we can get a little bit of that money because it was a personal application of Christopher and Helena as the co-chairs of the working group 12. But I think they will help us a little bit to, make Quareb LIMI a little bit more sustainable. I think I can jump over that and tell you just 2 things. So working together with the industry, because this is important. In the end, if we do not have the industry in the boat, it will never work. Also the data management stuff, it will not work because we will not write all the time again and again bioformats, translators and so on. People think, oh, AI will solve the problem. I think we should not rely on AI at that point. And when you talk with the experts, they are quite skeptical. So what we try to do, we try to catch areas in microscopy, and there we collect all the experts from the companies, Andor, Hamamatsu, PCO, Roper, Teledyne, also the microscope companies which have OEM cameras. So that was all about cameras. And we succeeded. You can read that also, how we did this in 2 editorials in Nature Methods, on agreeing on a common language which will be used for the data sheets and for the measurements of the cameras. And currently we are working on a glossary because you have to explain what do you mean with a certain expression when you use it. And that is, I think, very successful, and we are near to finish that. And then other things are writing macros. Yeah, we have macros where you can just place a power meter on the microscope. You set up what you want to measure, and you can measure all your lasers. You can define you want to have a short time or a long time measurement. You want to measure linearity, and it does it. You can leave the microscope alone for half an hour or maybe for a day. It depends on what you are interested in. It works with, I think, the major power meter brands, what people are using from Tor Labs or from Ophir. And it controls the power meter as well as the microscope, switching filters, switching laser intensities, and so on. And we have that now for Zeiss, and we have that for Nikon. Leica is completely closed. They even claim they have no programming language for the Stellaris, which is a pity for us, because that means, yeah, you have to do it by hand. Okay, so the final part is, what can we do with ISO? So we were told by the companies to get resources within a company. It's always a difficult thing. So that a company dedicates a person to a project, you have to have a reason. Yeah, and very often we did this, going to the company, talking with the people, and it's difficult and lasts long. But they told us, oh, if there is an ISO norm, which is coming out, then we have to obey the ISO norm. This means within 1 or 2 years, there is then the rule, oh, you have to follow the ISO rules. And that's now our current topic. And I think, so Orestes, I could convince him to join. Actually, you have to join first the local national body for standardization, and then you can join ISO. Laurent Gehlmann, Arne Seitz, they joined actually DIN, because in Switzerland they would be quite alone. But they are now in DIN, which is the German standardization, and then they are in ISO. And we meet in ISO, the next ISO meeting will be actually in Switzerland. And then there come from all over the world, there come the people from Japan, from Olympus, from Evident, Evident, and from Nikon, Leica and Zeiss. They all come also during the year. We have online meetings and we work on topics. And one topic, which actually the last world meeting of ISO was in Boulder in October, and there I managed to press through. We will have a working, first it's named a preliminary working item about metadata for image acquisition. This is describing all the metadata, how you set up the microscope, what equipment is connected to the microscope. So that will be a coming ISO norm. And an ISO norm is like a rule. Yeah. So we have to work on that, and I'm just collecting people and make more or less an open call. If someone wants to work from France on that topic and have the chance actually to form, I would say, the future of the microscopy metadata, please contact me, or the best is maybe Orestes, because Orestes knows how to join the France standardization body, and then you can work in ISO. We work also on, for example, multi-well plates. So we try to make a new standard for, there is an ANSI standard, but that was made 20 years ago when no one was using multi-well plates in microscopy. So you all know they are horrible. They have different heights. They are not flat, the bottoms. And this is something, if you write it in an ISO norm, companies will follow and bring out plates which follow these rules. Okay? In the end, what we want to have fair data, findable, accessible, interoperable, reusable. And we do, I think, a lot in Quareb Limi to achieve this aim. Thanks a lot. If you want to join, just go to the website. There's a form which you can fill out and be part of Quareb. Thanks.